Our galaxy, a place filled with countless mysteries and wonders beyond our wildest imaginations, holds secrets that continue to elude even the most brilliant minds. But it's not the only one. Stretching far beyond what we can comprehend, our galaxy is merely a small speck in an unimaginable expanse. With potentially hundreds of millions of other galaxies waiting to be discovered, the true enormity of the cosmos remains largely untouched. These galaxies, each unique and incomprehensibly vast, hold their own puzzles, intricate and tantalizing, and yet they all share one common thread: the greatest unanswered question of them all. How did these colossal systems form from what appears to be nothing? How did chaos and void give birth to such incredible order? The universe, an ever-expanding mix of galaxies, stars, planets, and myriad forms of matter and energy, presents a profound mystery that has captivated humanity for centuries. At the heart of modern cosmology is the understanding that the universe began approximately 13.8 billion years ago with the Big Bang, a colossal explosion that marked the inception of everything we know. This monumental event set into motion the expansion of space, creating the vast and intricate cosmic web we observe today. It is this continuous expansion that drives our quest to understand the origins of the universe and the forces that shape it. However, scientists have only begun to scratch the surface of this cosmic puzzle. Through their observations, they've revealed that ordinary matter, the very substance that makes up stars, planets, and living beings, constitutes a mere 5% of the universe's total mass and energy. The remaining 95% is a mysterious concoction of dark matter and dark energy, invisible forces that govern the structure and expansion of the universe, yet evade direct detection. This astonishing revelation deepens the mystery as we continue to probe the hidden corners of the cosmos in search of answers. The vastness of the universe is almost beyond comprehension, stretching over billions of light years across. Within this immense expanse, there are an estimated 2 trillion galaxies, each one home to billions of stars and untold planets. When viewed from this perspective, the Earth becomes but a tiny speck in the grand tapestry of existence. This realization humbles us, making us question our place in the universe and the forces at play on a scale so grand that it challenges the limits of human understanding. The laws of physics, consistent throughout the universe, govern everything from the motion of galaxies to the life cycle of stars and the intricate dance of particles at the quantum level. These laws have allowed scientists to predict cosmic phenomena with astonishing accuracy, from the paths of planets to the behavior of black holes. Those enigmatic entities whose gravitational pull is so strong that not even light can escape. But while the laws of physics have unlocked many of the universe's secrets, they also raise new questions, particularly regarding dark energy and its role in the acceleration of the universe's expansion. This discovery, made through observations of distant supernovae, revealed that dark energy is working against the gravitational pull of matter, driving galaxies apart at an accelerating rate. This raises profound implications for the future of the universe, suggesting a scenario where galaxies will drift ever farther apart, leading to a cold and empty cosmos. The impact of dark energy on the universe's fate is still a subject of intense debate, yet it points toward a future where the very fabric of the cosmos continues to evolve in ways we can scarcely imagine. The Big Bang Theory stands as a cornerstone of modern cosmology, offering a compelling explanation for the origin and evolution of the universe. According to this theory, the universe began as an incredibly hot and dense point around 13.8 billion years ago, and it has been expanding ever since. This notion is supported by a wealth of scientific evidence, including the discovery of cosmic microwave background radiation, a faint glow that serves as a snapshot of the universe just 380,000 years after the Big Bang. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, this radiation confirms the predictions of the Big Bang Theory and offers a clear imprint of the universe's early hot, dense state. Further backing the Big Bang Theory is the observation of the redshift of galaxies. This phenomenon indicates that galaxies are moving away from us and, by extension, from one another. This groundbreaking discovery, made by Edwin Hubble in the 1920s, revealed that the universe is not static but is in a state of continuous expansion. Hubble's law dictates that the farther a galaxy is from us, the faster it seems to be receding, a relationship that supports the core tenets of the Big Bang theory. Additionally, the theory elegantly accounts for the relative abundances of light elements such as hydrogen, helium, and lithium found in the universe. According to Big Bang nucleosynthesis, these elements were forged in the first few minutes after the Big Bang, as the universe cooled sufficiently for protons and neutrons to combine into atomic nuclei. The abundance of these elements in the cosmos closely matches predictions made by the theory, offering further support for its validity. Despite its widespread acceptance, the Big Bang theory also raises profound questions that remain unanswered. For example, it does not explain what preceded the Big Bang or what lies beyond the observable universe. Additionally, the theory introduces the concept of cosmic inflation, a period of rapid expansion that occurred fractions of a second after the Big Bang. This inflationary period solved several cosmological puzzles, such as the horizon and flatness problems, and predicted that the universe should appear flat and uniform on large scales, which is consistent with current observations. As the universe expanded, it cooled, and gravity began to shape the distribution of matter, pulling particles together to form the first stars and galaxies. These cosmic structures acted as furnaces, fusing lighter elements into heavier ones, and releasing these elements into space when they perished, enriching the universe with the building blocks for planets and life. This process continues today, with new stars being born while others fade into black holes, neutron stars, and remnants of once glorious celestial bodies. One of the most fascinating aspects of the universe's expansion is the discovery that it is accelerating. This revelation, driven by the mysterious force known as dark energy, suggests that space itself is stretching at an ever-increasing rate. Dark energy exerts a repulsive force that opposes the gravitational pull of matter, pushing galaxies apart at an accelerating pace. While the exact nature of dark energy remains one of the greatest mysteries in modern cosmology, understanding its role in the universe's future is crucial to comprehending the ultimate fate of the cosmos. The journey of the universe, from the explosive birth of the Big Bang and to the ongoing expansion driven by dark energy, continues to challenge our understanding of the cosmos. Each new discovery brings us closer to unraveling the mysteries that lie beyond the stars, but it also raises new questions, inviting future generations of scientists to explore deeper and seek answers to the ultimate questions of existence. How did the universe begin? What lies beyond our observational limits? And ultimately, what is the destiny of the cosmos as it expands ever outward? These questions remain at the forefront of our quest for knowledge, driving the unrelenting curiosity that defines humanity's search for the truth about the universe. The first second after the Big Bang marked a period of unimaginable transformation that set the foundation for the universe as we know it. Picture this. At the very moment of creation, the universe was concentrated into an intensely hot and dense point. This explosive beginning triggered a rapid expansion in an event known as inflation. Within fractions of a second, the universe grew from being smaller than an atom to a size larger than a galaxy, all in less than the blink of an eye. During this phase, temperatures soared to extremes, reaching billions of degrees. As the universe expanded, it began to cool down, creating the conditions for the fundamental forces of nature to begin separating from each other. At the outset, all four forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. But as the universe cooled, they began to split apart, each taking on its distinct role. Gravity was the first to separate from the grand unified force, followed by the strong nuclear force splitting from the electroweak force, a combination of electromagnetism and the weak nuclear force. This separation marked a pivotal moment in the universe's evolution, as it shifted from a unified state to the diverse forces we recognize today. In the first fraction of a second, the universe cooled enough to allow quarks, the building blocks of protons and neutrons, to begin forming. Initially, these quarks existed as free particles, but as the temperature dropped, they started to combine and form protons and neutrons. This crucial process, known as baryogenesis, was fundamental to the formation of the matter that would eventually make up stars, planets, and galaxies. Meanwhile, The universe was filled with a dense, hot plasma of quarks, electrons, and neutrinos. The expanding and cooling universe led to the formation of stable quark combinations, setting the stage for the creation of the first elements. By the end of the first second, the universe had cooled enough for the basic forces to take their present forms and for the first building blocks of matter, protons and neutrons, to emerge. Though still incredibly hot and dense compared to today, this moment marked the beginning of the universe's gradual transformation from a chaotic soup of particles to the complex cosmos we observe today. As the universe continued to cool, the interaction between quarks became a defining feature in the early universe's evolution. Quarks, although fundamental to matter, cannot exist independently due to their incredibly small size. Instead, they are always found in groups. This is evident in how they bind together to form larger particles like protons and neutrons, which make up the atomic nucleus. But how did this happen? It takes us to the very start of the universe during the quark epoch, which occurred in the first microsecond after the Big Bang. At this time, the universe was so hot and dense that the laws of physics as we know them didn't apply. The extreme temperatures in the trillions of degrees resulted in a state known as a quark-gluon plasma, a soup of quarks and gluons, particles that act as the glue holding quarks together. As the universe expanded and cooled rapidly, quarks began combining into protons and neutrons, a process that required temperatures to drop low enough for the strong nuclear force to take effect. The strong nuclear force, one of the four fundamental forces of nature, is incredibly powerful but operates only over very short distances. It was this force that allowed quarks to stick together, forming composite particles like mesons made of one quark and one antiquark, and baryons made of three quarks. Protons and neutrons, which are baryons, became the building blocks for atomic nuclei. This transition from quarks to protons and neutrons was essential in the formation of atoms, stars, and galaxies. Once protons and neutrons were stable, they began to bond, forming the nuclei of the first elements, leading to nucleosynthesis. This process was a precursor to the chemical complexity that allowed for the eventual formation of stars, planets, and life as we know it. The quark epoch and the subsequent formation of protons and neutrons were key milestones in the universe's journey from a chaotic, high-energy state to the familiar world of matter and structure we live in today. During the quark epoch, the universe existed as an incredibly hot, dense soup of quarks and gluons. Quarks are the fundamental building blocks of matter, and they come in 6 distinct types, or flavors: up, down, charm, strange, top, and bottom. However, for protons and neutrons, particles that make up the nuclei of atoms, only up and down quarks are involved. The role of gluons in this epoch is crucial. These particles act as the carriers of the strong nuclear force, the fundamental force that holds quarks together. Despite the natural repulsion between quarks due to their charges, gluons bind them together, allowing the formation of stable particles. As the universe expanded and cooled after the Big Bang, it eventually reached a temperature low enough for quarks to begin combining into more stable forms. This process took place around 1 microsecond after the Big Bang, and marked a key transition in the early universe's evolution. The cooling allowed the strong nuclear force to become dominant over the thermal energy, which had been preventing quarks from sticking together. Once the strong force took hold, quarks started binding into groups called hadrons. These groups included protons and neutrons, the building blocks of atomic nuclei. A proton is composed of 2 up quarks and 1 down quark, while a neutron is made up of 2 down quarks and 1 up quark. These specific combinations give protons and neutrons their distinctive properties. For example, protons are positively charged, while neutrons carry no charge. This distinction is fundamental in the creation of matter as we know it, as it governs how atoms and molecules will form and interact in the future. The formation of protons and neutrons was crucial in transforming the quark-gluon plasma into the matter-filled universe we observe today. With protons and neutrons in place, the next step was the formation of atomic nuclei in a process known as nucleosynthesis. This began the creation of the simplest elements like hydrogen and helium, which would eventually lead to the formation of stars, galaxies, and life. The quark epoch also introduces the idea of symmetry breaking, a process that occurred as the universe cooled and the forces that shaped it began to differentiate. Initially, all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. However, as the universe expanded and cooled, this unified force began to break apart, a phenomenon known as symmetry breaking. The first force to separate was gravity, despite being the weakest of the four. Gravity plays a key role in shaping the large-scale structure of the universe by influencing the motion of galaxies and clusters. Though weaker at smaller scales, gravity's influence grows with mass and distance, making it the dominant force on cosmic scales. The next force to separate was the strong nuclear force. This force is responsible for holding atomic nuclei together, overcoming the repulsive electromagnetic force between positively charged protons. As gravity separated first, the strong nuclear force came next, facilitating the combination of quarks into neutrons as described earlier. This allowed the formation of stable atomic nuclei, which would later form the basis of matter. Following the strong nuclear force and electromagnetism separated, the weak nuclear force plays an essential role in nuclear fusion and radioactive decay. It governs the life cycles of stars and the synthesis of elements heavier than hydrogen. Electromagnetism, the force behind light, electricity, and magnetism, governs interactions between charged particles. It shaped the behavior of atoms and molecules, influencing the chemistry that underpins all forms of life. These four fundamental forces acted as architects of the universe, guiding the raw materials created in the aftermath of the Big Bang into the complex and diverse cosmos we see today. As the universe cooled further, processes like recombination occurred, allowing atoms of hydrogen and helium to form. This led to the universe becoming transparent to light, allowing the cosmic microwave background, CMB, radiation to be released. The CMB is a remnant from this era, providing us with a snapshot of the infant universe. The interplay between the forces also led to the formation of stars and galaxies. Gravity helped clump matter together, while the strong nuclear force, weak nuclear force, and electromagnetism played pivotal roles in the internal processes of stars. These forces powered stars, enabling nuclear fusion, and contributed to the creation of heavier elements essential for life and planets. The early universe's rapid expansion and cooling laid the groundwork for the complex structure of the cosmos, transforming it from an inhospitable, chaotic state into the vibrant universe that we observe today. Through the interplay of fundamental forces and the formation of the first stable particles, the foundation was set for all that would follow, from the creation of galaxies to the emergence of life itself. Delving deeper into the mysteries of the universe, we shift our focus toward one of the most significant milestones in cosmic history, the formation of the very first atoms. This pivotal event, known as recombination, occurred approximately 378,000 years after the Big Bang. Before this epoch, the universe was in a state of dense, hot plasma composed of electrons, protons, and photons. The temperatures were so extreme that atoms could not form, as any attempt at formation would result in the particles being ripped apart by the rampant energy of the time. As the universe expanded, it gradually cooled, allowing the temperature to drop enough for these particles to bond. Hydrogen, the simplest and most abundant element in the universe, was the first atom to form. Comprising just one proton and one electron, hydrogen marked the dawn of a new era in cosmic evolution. Following closely behind, helium atoms began to form. Slightly more complex, helium consists of 2 protons, 2 neutrons, and 2 electrons. These early atoms laid the foundation for the chemical diversity we see across the universe today. With the formation of these atoms, the universe began to take shape in a way that would eventually lead to the formation of stars, galaxies, and other cosmic structures. The formation of the first atoms was not just a significant event in itself, but also set the stage for a critical turning point, the formation of the first molecules. This transition from isolated atoms to the earliest molecules marked a profound step forward in the universe's chemical evolution. As the universe cooled and expanded further, conditions gradually became favorable for interactions between atoms, primarily hydrogen and helium. These atoms began to bond in novel ways, paving the way for more complex chemical reactions. Hydrogen, with its single electron, was particularly predisposed to forming bonds with other hydrogen atoms. This led to the formation of molecular hydrogen, H2, a critical step in the evolution of the cosmos. Though molecular hydrogen was simple in structure, it played a pivotal role in the early universe's chemistry. H2 served as a coolant, enabling gas clouds to collapse more efficiently under gravity. This collapse allowed for the formation of the first stars, massive, hot, and short-lived, but crucial to the next phase of cosmic evolution. In these nascent stars, the first heavy elements would be forged, elements that would eventually contribute to the creation of planets, asteroids, comets, and all living organisms. The exact timeline for the formation of the first molecules is still the subject of ongoing research, but it is believed that molecular hydrogen began to form just a few 100,000 years after the Big Bang, shortly after atomic formation. This period was crucial, as it set the stage for the intricate processes that would lead to the formation of galaxies, stars, and planets. It also marked the beginning of the complex chemical reactions that would eventually give rise to the building blocks of life itself. Helium and hydrogen played instrumental roles during this phase of the universe's evolution. These two elements, the simplest and most abundant in the cosmos, were foundational to the universe's chemistry and structure. After the Big Bang, the universe was predominantly filled with hydrogen and helium. Hydrogen, with its simplicity and abundance, formed the bulk of the universe's matter. Helium, slightly heavier, was the second most abundant element. Their simplicity made them the perfect building blocks for the emergence of more complex elements and molecules, which would later be synthesized through nuclear processes within stars. The role of hydrogen went far beyond its abundance. Hydrogen was a key ingredient in the formation of the universe's first stars, known as population 3 stars. These stars were massive, hot, and short-lived. Despite their brief existence, they were critical to the synthesis of heavier elements through nuclear fusion. As these first stars exploded in spectacular supernovae, they scattered these newly formed heavier elements throughout the universe, seeding the cosmos with the raw materials necessary for the creation of new stars, planets, and eventually life. Helium's role in the universe's early chemistry, while less directly involved in chemical complexity, was still significant. Helium influenced the evolution of stars, as it is the product of hydrogen fusion in the cores of stars. This fusion process releases vast amounts of energy and light, powering stars and contributing to the creation of elements in their cores. Over time, stars began to fuse helium into heavier elements, a process that led to various stellar outcomes, such as supernovae and the formation of black holes. These processes were essential for creating the diversity of astronomical objects we observe today. Moreover, the ratio of hydrogen to helium in the universe offers critical insights into the conditions of the early universe and provides strong support for the Big Bang theory. Observations of the primordial helium abundance, coupled with the cosmic microwave background (CMB) radiation, provide compelling evidence of the hot, dense origins of the universe, marking its transition from a chaotic plasma state to the more structured cosmos we know today. These early atoms and molecules were the first steps in the creation of the universe's chemical richness. They were the building blocks upon which stars, galaxies, and eventually life itself would be constructed, and they remain fundamental to the universe's ongoing evolution. From hydrogen and helium, the seeds of complexity were sown, leading to the creation of the universe's first stars, planets, and everything in between. The journey of these simple elements is the story of how the universe, once a hot and chaotic soup, slowly transformed into the vast and intricate cosmos we see today. As we continue our journey through the cosmos, the discovery of the cosmic microwave background, CMB radiation, serves as a profound reminder of the universe's ancient origins and the indelible traces left behind by the Big Bang. This afterglow, discovered in 1965 by Arno Penzias and Robert Wilson, offers us a window into the universe's earliest stages, at a time when it was just a few 100,000 years old. In essence, the CMB radiation is the faint glow of energy released during the epoch of recombination, when the universe had cooled enough for electrons and protons to come together to form neutral hydrogen atoms. Before this transformative moment, the universe existed as a hot, dense plasma, composed of electrons, protons, and photons. The intense heat and density of the early universe kept photons from traveling freely, as they were constantly scattered by free electrons. However, as the universe expanded and cooled, these photons were no longer scattered, allowing them to travel across vast distances without obstruction, thus creating the CMB radiation we observe today. This radiation, having been stretched to microwave wavelengths by the universe's ongoing expansion, provides us with an invaluable snapshot of the universe's infant years. One of the most remarkable aspects of the CMB is the subtle temperature fluctuations observed within it. These minute differences in temperature are thought to represent variations in the density of matter, marking the earliest seeds from which all present-day structures, like galaxies and clusters of galaxies, began to form. The study of these fluctuations has provided scientists with crucial information, helping to determine the fundamental parameters of our universe, such as its age, composition, and expansion rate. According to CMB measurements, the universe is approximately 13.8 billion years old, and its composition consists of about 5% ordinary matter, 25% dark matter, and 70% dark energy. These figures reveal the mysterious nature of the universe, dominated by invisible components that govern cosmic dynamics. Venturing deeper, the CMB's confirmation of the Big Bang theory is indisputable. The uniformity of the CMB's temperature, measuring roughly 2.7 Kelvin, minus 270.45 degrees across the sky with slight irregularities in temperature, corroborates the prediction that the early universe was in a hot, dense state. This cosmic radiation is not just a relic of the Big Bang. It is evidence of the universe's expansion from that primordial state, showing us how the cosmos evolved over billions of years. Experiments and observations using satellites such as COBE, WMAP, and Planck have provided precise measurements of the CMB, helping scientists track the universe's evolution from a hot plasma to the vast, complex structure we observe today. The CMB data has also been instrumental in verifying the inflationary theory. This theory posits that in the first moments after the Big Bang, the universe underwent an exponential expansion, smoothing out any irregularities and resulting in the relatively uniform universe we see now, with subtle density fluctuations that gave rise to galaxies. The CMB's temperature patterns offer key evidence for this rapid expansion, supporting the notion that the universe's early moments were crucial in shaping its large-scale structure. In addition to confirming the Big Bang theory and shedding light on the universe's structure, the CMB has inspired investigations into new physics. The discovery of anomalies like the cold spot has prompted further inquiries into aspects of the universe that remain poorly understood, inviting new theories that could potentially extend or challenge current models of cosmology. Thus, the cosmic microwave background radiation serves as a cosmic treasure trove, offering insights into the universe's infancy, evolution, and the forces that have shaped it. Its study continues to deepen our understanding of the cosmos and provides an essential foundation for future explorations into the nature of space, time, and the very fabric of the universe itself. As the afterglow of the Big Bang began to fade, the universe entered a period known as the Cosmic Dark Ages. This era, which lasted for about 380,000 years to 1 billion years after the universe's inception, was a time when the cosmos was veiled in a dense cooling fog of hydrogen gas. This made the universe opaque, preventing light from traveling freely through space. The absence of stars or galaxies left the universe in an eerie silence and darkness, marking a pivotal chapter in cosmic history. For this stretch of time, the universe was an invisible, hidden place. The cosmic dark ages were far from a void in the universe's evolution. They were a crucial period in which the groundwork for the universe's future was being laid. As the universe expanded, the primordial hydrogen gas began to clump together due to the force of gravity. These regions of higher gas density would eventually become the nurseries for the first stars, population 3 stars. These celestial bodies were unlike any stars we see today. They were massive, luminous, and short-lived, consisting almost entirely of hydrogen and helium. The nuclear fusion reactions within these stars released vast amounts of energy, reionizing the surrounding hydrogen gas. This process, known as cosmic reionization, pierced the opaque veil of the cosmic dark ages, leading the universe into a new era of transparency and light. With the birth of the first stars, the once dark universe began to light up. These stars ignited a transformative process, marking the end of the cosmic dark ages. The light from these early stars traveled through the cosmos, gradually illuminating the vast expanse and giving birth to the first galaxies. For astronomers and cosmologists, this period is of intense interest, as it holds valuable clues to the formation of the universe's first structures and to the nature of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, but exerts a powerful gravitational pull. Studying this era presents significant challenges because the light from this period is exceedingly faint and difficult to detect. However, advances in technology, particularly with next-generation telescopes, are enabling scientists to gradually peer into this elusive chapter of cosmic history. Observations of distant quasars and galaxies, combined with the cosmic microwave background radiation, a relic from the Big Bang, provide crucial insights into the nature of the early universe. These findings are shedding light on the cosmic dark ages and helping us understand the fundamental processes that have shaped the universe from its earliest moments. Roughly 100 million years after the Big Bang, the universe underwent a transformative phase that marked the birth of the first stars. The universe had previously been a homogeneous soup of hydrogen and helium gas, but subtle fluctuations in density began to form pockets of gas that were slightly more concentrated. These fluctuations were possibly amplified by dark matter, an unseen yet significant force that pervades the cosmos. Gravity took hold of these denser regions, pulling the gas inward, and as the clouds of gas grew denser and hotter, they reached a critical threshold. This was when the first stars ignited, primarily composed of hydrogen and helium. These early stars were giants compared to modern stars, burning with such intensity that their lifespans were relatively brief on a cosmic scale. The birth of these first stars ended the cosmic dark ages, introducing light back into the universe. These stars did not remain isolated. Under gravity's relentless pull, they began to clump together and form the first galaxies. These early galaxies were smaller and less structured than the galaxies we see today, but they laid the foundation for the large, majestic galaxies that would eventually form. The first stars, as they aged, played a key role in enriching the universe with heavier elements. The nuclear fusion processes within their cores forged elements like carbon, oxygen, and iron, materials that had never existed before. When these stars reached the end of their lives, they expelled these heavy elements into space through dramatic supernova explosions. These explosions seeded the cosmos with the building blocks necessary for future generations of stars, planets, and eventually, life. The formation of the first stars and galaxies marked the beginning of a complex series of events that shaped the universe's evolution in profound ways. These early stars emitted intense radiation, which played a pivotal role in reionizing the surrounding hydrogen gas, clearing the fog of the early universe. This process, known as cosmic reionization, took place span of several hundred million years, starting around 150 million years after the Big Bang and lasting until roughly a billion years after. This gradual process was essential for transforming the opaque, hydrogen-filled cosmos into the transparent starlit universe we observe today. The birth of the first stars and galaxies didn't just light up the cosmos, it also set in motion a deeper cosmic framework that would guide their formation and distribution. At the heart of this invisible structure lies dark matter, an essential yet mysterious component of the universe. Unlike ordinary matter, which interacts with electromagnetic forces and emits or reflects light, dark matter is completely invisible to our current observational instruments. It doesn't interact with light or other forms of electromagnetic radiation, making it impossible to detect directly. Despite its elusive nature, dark matter plays an absolutely crucial role in the formation of large-scale cosmic structures, such as galaxies and galaxy clusters. It is estimated that dark matter constitutes about 85% of the total matter in the universe, a staggering figure that highlights its influence on cosmic evolution. The presence of dark matter was first inferred from its gravitational effects on visible matter. For example, galaxies spin so rapidly that without an unseen mass to provide additional gravitational pull, they would tear themselves apart. Moreover, the way galaxies cluster together as well as patterns observed in the cosmic microwave background radiation. The afterglow of the Big Bang suggests there is far more matter in the universe than can be directly observed. These gravitational effects pointed to the existence of dark matter, even though it cannot be seen or directly measured. Dark matter played a critical role in the formation of the universe's first structures. In the early universe, tiny fluctuations in density became the seeds for larger structures to form. While ordinary matter, which makes up stars, planets, and gas clouds, is affected by all fundamental forces, dark matter interacts only through gravity. This made it uniquely suited to clump together in these denser regions, forming vast halos that acted as gravitational wells, drawing in the surrounding normal matter, mainly hydrogen and helium. These halos of dark matter provided the necessary gravitational framework for the gas to cool, condense, and form the first stars. As these stars began to coalesce into the first galaxies, they followed the distribution of dark matter, shaping the large-scale structure of the universe. This resulted in a cosmic web of galaxies and galaxy clusters, intricately linked by filaments of matter and vast voids between them. The structure of the universe as we see it today closely mirrors predictions made by simulations that incorporate dark matter. These simulations predict a cosmic web-like structure with galaxies and galaxy clusters woven into intricate patterns. The observational evidence supports these simulations, confirming that dark matter played a foundational role in shaping the universe's large-scale structure. However, despite our increasing understanding of dark matter's gravitational effects, its true nature remains one of the most intriguing mysteries in modern science. Scientists continue to explore various theoretical candidates for dark matter, ranging from WIMPs, weakly interacting massive particles, to axions, particles that are much lighter than electrons. Even with extensive searches, dark matter particles have yet to be detected directly, making it one of the most exciting and elusive fields of study in both cosmology and particle physics. Following the threads woven by dark matter in the cosmic tapestry, we witness the formation of stars as a natural progression in the universe's grand narrative. Stars begin their lives within vast, cold clouds of gas and dust, known as molecular clouds or nebulae. These clouds are primarily composed of hydrogen, with smaller amounts of helium and trace quantities of heavier elements. Within these nebulae, denser regions begin to form, often triggered by the gravitational influence of dark matter, nearby supernova explosions, or even the collision of gas clouds. When these regions of higher density reach a critical mass, gravity overpowers the internal forces resisting collapse. The cloud begins to contract, and as it does, the material at its center becomes increasingly dense and hot. This process, though it may take millions of years, is the crucial first step in the birth of a star. As the cloud continues to collapse, it forms what is known as a protostar, an intensely hot core that is the precursor to a full-fledged star. The protostar continues to gather mass from its surrounding environment, with the temperature in its core rising steadily. Once the temperature reaches around 10 million degrees Celsius, nuclear fusion begins. During fusion, hydrogen nuclei merge to form helium, releasing a tremendous amount of energy in the process. This burst of energy marks the birth of a new star. As fusion takes hold, it halts the gravitational collapse of the cloud, establishing a delicate balance between the inward pull of gravity and the outward pressure generated by the energy produced through fusion. This balance is what sustains the star, enabling it to shine for millions to billions of years. The size and mass of the star that forms depend on the amount of material it gathers before nuclear fusion ignites. More massive stars form from denser or larger molecular clouds and have shorter lifespans because they burn through their fuel much faster. In contrast, smaller stars, like our Sun, burn their fuel more slowly, granting them longer lifespans. Star formation rarely occurs in isolation. Within a single molecular cloud, many stars can form at once, leading to stellar clusters or associations. These clusters are gravitationally bound for a time before the stars eventually disperse. This communal birth of stars not only underscores the dynamic nature of the universe, but also highlights the interconnectedness of cosmic phenomena. Each star's birth contributes to the chemical enrichment of the universe, enriching the cosmos with the essential elements that will eventually form planets and potentially support life. The life cycle of a star is a fascinating journey that spans millions to billions of years. It begins in the cold, dense cores of molecular clouds, where gravity induces the collapse of gas and dust into protostars. When nuclear fusion ignites in their cores, stars are born. The process of star formation exemplifies the incredible complexity and interdependence of the universe's many forces and phenomena, shaping the very fabric of cosmic evolution. The path a star takes through its lifetime is profoundly influenced by its initial mass, shaping its evolution and ultimate fate. Smaller stars like our Sun enter the main sequence phase after their birth, a stage that constitutes the majority of a star's life. During this phase, hydrogen fusion occurs in the core, producing helium and releasing energy that prevents the star from collapsing under its own gravity. For a Sun-like star, this phase can last about 10 billion years. As hydrogen in the core is gradually depleted, the star's life takes an extraordinary turn. When the hydrogen in the core is exhausted, fusion halts and gravity begins to contract the core. This contraction heats up the core, causing hydrogen fusion to occur in a shell around the helium-rich core. The energy output from this fusion causes the outer layers of the star to expand and cool, transforming it into a red giant. During the red giant phase, the star's outer layers can engulf nearby planets, dramatically altering the structure of its solar system. This phase marks a critical turning point in a star's life, where its size and luminosity increase exponentially. The final stages of a star's life depend on its mass. For stars with a mass up to about 8 times that of the Sun, the core eventually sheds its outer layers, creating a planetary nebula, a glowing shell of gas. The remnant core becomes a white dwarf, a dense, hot object roughly the size of Earth, which will gradually cool and fade over billions of years. In contrast, more massive stars face a more violent demise. These stars go through successive stages of nuclear fusion, burning through layers of elements until their cores collapse. This collapse leads to a supernova explosion, a cataclysmic event that briefly outshines entire galaxies and is responsible for producing and dispersing heavy elements across the universe. The remnants of a supernova can form a neutron star, an incredibly dense object only a few kilometers across but with more mass than the Sun. Or, if the star is massive enough, a black hole, a region of space with gravity so intense that not even light can escape. The death of a star, particularly in a supernova explosion, plays a vital role in the cosmic cycle by creating and distributing the elements essential for life, such as carbon, oxygen, and iron. One of the most remarkable aspects of a star's life cycle is its ability to produce heavier elements through a process called nucleosynthesis. Stars fuse hydrogen into helium in their cores, which powers their energy output and provides the light and heat we associate with stars. As stars evolve, particularly those more massive than the Sun, their cores reach such extreme conditions that they fuse heavier elements like carbon, oxygen, silicon, and iron. These elements are forged under immense pressure and temperature in the cores of massive stars or within the explosive environments of supernovae. For instance, carbon is formed by the fusion of 3 helium nuclei, requiring temperatures exceeding 100 million degrees Celsius. The process continues with heavier elements being formed, with iron being the final and most stable product. Iron, however, does not release energy when fused. It consumes energy. As a result, when the core of a massive star turns to iron, the fusion process can no longer counteract gravity, leading to the star's collapse and the subsequent supernova explosion. This cataclysmic event is responsible for creating the heaviest elements, including gold, uranium, and plutonium. These elements are scattered across space, enriching the cosmos and ensuring the continuous cycle of stellar birth, death, and rebirth. The iron in our blood, the calcium in our bones, and the oxygen we breathe are all products of ancient stars. This cosmic recycling ensures that the elements needed for life are not locked away within the interiors of dying stars, but are instead spread across the universe. As a result, the death of a star is not an end, but a necessary step in the ongoing evolution of the cosmos, seeding the universe with the raw materials needed to form new stars, planets, and potentially life itself. Supernovae, in particular, are responsible for creating and distributing many of the heavy elements that make life as we know it possible. These stellar explosions play a pivotal role in the cosmic tapestry, driving the evolution of the universe and fostering the conditions for the birth of new worlds. Delving into the cosmic ballet of galaxy formation, we embark on a journey that stretches across billions of years, where the universe's fundamental forces choreograph the creation of these colossal celestial entities. Galaxies, vast islands of stars, gas, dust, and dark matter are the fundamental building blocks of the cosmos. Their formation is a tale of both simplicity and complexity, woven together by the laws of physics. In the beginning, following the Big Bang, the universe was an extremely hot, dense sea of particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms. This era, known as a recombination, marked a pivotal moment in cosmic history. The universe transitioned from being opaque to transparent, allowing light to travel freely for the first time. However, even in this nascent universe, it was far from perfectly uniform. Subtle density fluctuations or ripples in the fabric of space-time left over from the Big Bang set the stage for the formation of galaxies. Gravity, the great sculptor of the universe, took center stage, amplifying these tiny fluctuations. Regions that were slightly denser than their surroundings began to attract more and more matter, growing progressively more massive. This process is beautifully illustrated by the concept of gravitational collapse, where vast gas clouds, mostly composed of hydrogen, began to collapse under their own gravity. As these clouds condensed, they formed the first stars and protogalaxies, early, simpler structures that would later evolve into the complex galaxies we observe today. However, the story of galaxy formation is not solely the result of gravity's inward pull. Other forces played equally crucial roles, most notably dark matter. This mysterious substance, which neither emits nor absorbs light, exerts a gravitational influence on visible matter. Dark matter makes up about 85% of the universe's total matter and acted as scaffolding for galaxy formation. In the early universe, dark matter clumped together by creating dense gravitational wells into which ordinary matter could fall, thus accelerating the process of galaxy assembly. In addition to dark matter scaffolding, feedback processes also influenced the evolution of early galaxies. Energy from star formation and violent supernova explosions generated powerful outflows of gas, which heated and expelled material from the forming galaxies. These energetic expulsions prevented gas from cooling and collapsing too quickly, regulating the pace of star formation. This feedback mechanism ultimately led to the diverse range of galaxy sizes and shapes we see today, from the graceful spiral galaxies like our Milky Way to the more spherical elliptical galaxies and the disorganized irregular galaxies. As galaxies grew and evolved, they did not do so in isolation. In the crowded environment of the early universe, galaxy collisions and mergers were common. These cosmic encounters could dramatically alter the structure of a galaxy, influencing its star formation rate and leading to new morphological features like spiral arms. Moreover, these mergers were instrumental in the growth of supermassive black holes at the centers of many galaxies. Today, galaxies continue to evolve, shaped by interactions with other galaxies, intergalactic gas, and the broader cosmic environment. The study of galaxy formation and evolution is more than a look into the past. It offers crucial insights into the fundamental processes that govern the universe. It is a narrative of creation, transformation, and interaction, highlighting the intricate dance of matter and energy that shapes the universe. In the vast expanse of the cosmos, galaxies are grand assemblies of stars, gas, dust, and dark matter, each presenting itself in a magnificent and unique form. These cosmic entities, numbering in the billions, come in various shapes and sizes and are classified into distinct types based on their structure. The three main types, spiral, elliptical, and irregular galaxies, each tell a different story of cosmic evolution and interaction. Spiral galaxies, like our Milky Way, are characterized by their flat, rotating disks of stars, gas, and dust, often with beautiful spiral arms. Elliptical galaxies, typically more spherical or elliptical in shape, lack the structure and star formation activity seen in spiral galaxies, often containing older, redder stars. Irregular galaxies, as their name suggests, are chaotic in shape and often result from gravitational interactions or mergers with other galaxies. Each of these galaxy types adds its unique chapter to the grand narrative of the universe's evolution. Spiral galaxies, such as our Milky Way, stand out for their distinctive, flat, disc-like shape, with sweeping arms radiating from a central bulge. This bulge is a dense collection of older stars that serves as the galaxy's core. The spiral arms, in contrast, are sites of active star formation where gas and dust, the raw materials for new stars, are concentrated. These arms often glow with the light of bright nebulae and young, hot stars, giving the galaxy its characteristic luminosity. The spiral structure is believed to be the result of density waves traveling through the galaxy, compressing gas and dust, and triggering star formation in a ripple-like effect. These waves move like traffic jams, creating regions of higher density and igniting the formation of stars wherever they pass. Elliptical galaxies, on the other hand, present a stark contrast to spiral galaxies. They lack the elegant, winding arms and the intricate structure of spiral galaxies. Instead, they exhibit a more rounded, often elliptical shape, ranging from nearly spherical to elongated forms. Composed predominantly of older, redder stars, elliptical galaxies are relatively devoid of gas and dust, and as a result, they experience very little new star formation. The lack of fresh star birth makes elliptical galaxies appear more barren compared to their spiral counterparts. Their size can vary greatly, from giant elliptical galaxies that dominate their local galaxy clusters to smaller dwarf elliptical galaxies that are often found orbiting larger galaxies. Many of these massive elliptical galaxies are thought to have formed from the merger of smaller galaxies, a process that strips away much of the gas and leaves behind a smooth, featureless structure. Irregular galaxies, as their name suggests, are the cosmic outliers, lacking the well-defined structure of spiral and elliptical galaxies. These galaxies appear chaotic in shape, with no discernible form, and they tend to be rich in gas and dust. This abundant material provides a fertile ground for star formation, and as a result, irregular galaxies often experience bursts of star creation. The irregularity of these galaxies is typically the result of gravitational interactions with other galaxies, which can distort their structure and trigger intense episodes of star formation. Irregular galaxies are important to astronomers because they offer a unique view into the processes of galaxy interaction and the evolution of galaxies in response to external forces. In addition to these broad categories, the universe also hosts a variety of subtypes and peculiar galaxies that challenge simple classification. For instance, lenticular galaxies, which sit between spiral and elliptical galaxies, have a prominent central bulge and a disk but lack spiral arms. These galaxies often appear as a hybrid form, offering insights into the transitional stages of galactic evolution. Other peculiar galaxies, the result of dynamic and sometimes violent interactions with neighboring galaxies, may exhibit a range of strange and irregular characteristics. These dynamic processes, including gravitational encounters and galactic mergers, emphasize the complexity of the universe's evolution and the forces that shape its structures. This diverse array of galaxy types underscores the ongoing complexity of cosmic evolution. It highlights how gravity, collision, and merger events influence the structure and evolution of the universe. Galaxies numbering in the billions are not only grand assemblies of stars, gas, dust, and dark matter, but they also represent a captivating and multifaceted history of cosmic interactions. Each type, whether spiral, elliptical, or irregular, tells a unique story of formation, transformation, and interaction, contributing to the ever-changing tapestry of the cosmos. The formation of galaxies is an intricate and dynamic process, and it often begins with the merging of smaller, primordial galaxies. These cosmic collisions, although destructive, play a pivotal role in shaping the structure of larger galaxies over billions of years. As galaxies collide, the interaction strips away gas and dust, leading to the formation of a smoother, less structured galaxy. This process often leaves behind irregular galaxies, which stand in stark contrast to their more orderly cousins, spiral and elliptical galaxies. Irregular galaxies, by their very nature, lack the symmetry and coherence that define spiral and elliptical galaxies. They are often chaotic in appearance, displaying a haphazard mix of gas, dust, and stars. Despite their disorderly structure, irregular galaxies are vital laboratories for astronomers, providing fertile grounds for star formation due to their rich reservoirs of gas. These galaxies are typically formed when gravitational interactions or collisions with other galaxies distort their structures, often sparking bursts of new star births. Such galaxies offer valuable insights into the mechanisms of galaxy evolution, helping scientists understand the complex interplay of forces that shape the universe. Beyond the traditional classifications of spiral, elliptical, and irregular galaxies, there exists a fascinating array of subtypes and peculiar galaxies that challenge our understanding of cosmic structure. One such example is the lenticular galaxy, a hybrid of sorts between the spiral and elliptical types. Lenticular galaxies possess a large central bulge and a disk, but lack the distinctive spiral arms that characterize spiral galaxies. This unique feature places them in a category that bridges the gap between the two more familiar forms. The diversity of galaxies, from the most orderly spirals to the most chaotic irregulars, reveals the complexity of cosmic evolution and the multitude of factors, gravity, collisions, and mergers, that contribute to the ever-changing structure of the universe. The formation of our own Milky Way galaxy is a dramatic tale of cosmic evolution, stretching across nearly 13.6 billion years. At the heart of this formation is the process of hierarchical assembly, a concept that underpins the evolution of galaxies throughout the universe. According to this principle, smaller components, whether clouds of gas or small protogalaxies, gradually merge to form larger and more complex structures. In the early universe, a sea of hydrogen, helium, and traces of lithium existed in an otherwise formless expanse. However, tiny irregularities in the density of this primordial gas, likely influenced by the mysterious force of dark matter, slowly coalesced under the pull of gravity. Over time, these denser regions attracted more matter, evolving into the first protogalaxies, which would eventually merge to form larger galaxies. As the nascent Milky Way grew, dark matter played a crucial role in guiding the assembly of stars and gas into a more cohesive structure. Dark matter, though invisible, exerts a gravitational pull that can be detected through its effects on visible matter. Its presence was essential in helping the early Milky Way grow and evolve. The formation of the Milky Way's disk, a region where our solar system resides, was a gradual process that occurred over billions of years. As gas settled into the galactic plane, it spiraled inward, conserving angular momentum, and began forming new stars. These stars enriched the galaxy, producing heavier elements in their cores and spreading them throughout the galaxy. This ongoing process of stellar birth and death ultimately laid the groundwork for the formation of planets and life. At the heart of the Milky Way lies the bulge, a dense concentration of stars that includes some of the galaxy's oldest stellar populations. These stars formed early in the galaxy's history, during the initial stages of its formation. Surrounding the bulge is the disk, home to the Milky Way's iconic spiral arms, which are regions of active star formation. These arms trace their origins to density waves that ripple through the galaxy's disk, compressing gas and dust, which triggers the birth of new stars. As these stars shine brightly, they illuminate the arms, making them visible across vast stretches of space. This dynamic interplay of forces, gravity, gas, and dark matter, continues to shape the Milky Way, ensuring that it remains a vibrant and ever-evolving galaxy in the cosmos. The Milky Way, our vast and majestic galaxy, has been evolving for billions of years. From the time it first formed, it has been shaped by the constant process of accreting gas and merging with other galaxies. These cosmic events have gradually transformed it into the structure we see today. However, perhaps the most dramatic event on the horizon for the Milky Way is an impending collision with the Andromeda Galaxy, its nearest neighbor. This galactic merger, expected to occur in about 4 billion years, will redefine the Milky Way's place in the universe. As these two massive galaxies collide, they will merge to create an entirely new, much larger galaxy, an extraordinary moment in the ongoing cosmic dance of the stars. But as the Milky Way grows and evolves, it is not merely the result of interactions between stars and gas. It is also heavily influenced by an invisible yet immensely powerful force at its very heart, the supermassive black hole. These behemoths of gravity reside at the centers of nearly every large galaxy, including our own. Their influence is profound as they shape the evolution of galaxies through the immense gravitational forces they exert. With masses ranging from millions to billions of times that of the Sun, Supermassive black holes are both the anchors and architects of their galaxies, holding the cosmos together while simultaneously molding it in ways we are only beginning to understand. The connection between supermassive black holes and their host galaxies is a fascinating one, filled with complexity and mystery. Modern astrophysics has revealed a striking correlation between the mass of a galaxy's central black hole and key properties of the galaxy itself, particularly its bulge. For instance, a galaxy's bulge mass and velocity dispersion tend to align closely with the mass of its central black hole, suggesting that these two entities evolve in tandem. This discovery hints at an intrinsic relationship between the growth of the black hole and the development of the galaxy, almost as if the black hole plays an active role in shaping the galaxy's fate. The ways in which supermassive black holes influence their galaxies are profound and varied. One of the most significant effects is their ability to regulate star formation within their host galaxies. As matter falls into a supermassive black hole, it heats up and emits vast amounts of energy, often in the form of powerful radiation and energetic outflows. These outflows can have a dramatic impact on the surrounding gas, heating it to such extremes that it can no longer collapse to form new stars. In some cases, the radiation can even expel gas from the galaxy's core altogether, effectively halting the process of star formation. This self-regulation is crucial for maintaining the delicate balance of a galaxy's evolution, ensuring that star formation does not occur too rapidly and exhaust the galaxy's gas reserves prematurely. Moreover, this process is not limited to simply halting star formation. The energy released by a supermassive black hole as it devours matter can cause the surrounding gas to undergo a process known as reionization. During this process, the gas becomes so hot and energetic that it can no longer condense to form new stars, further limiting the galaxy's growth. This feedback mechanism plays a critical role in shaping the overall structure and size of galaxies, preventing them from growing too large by controlling the amount of cold gas available for star formation. In this way, the supermassive black hole not only governs the pace of star formation, but also ensures that the galaxy's evolution remains in harmony with its resources. In addition to their role in star formation, supermassive black holes also have a profound effect on the dynamics of their galaxies. The immense gravitational pull of a black hole can influence the orbits of stars within the galaxy's core, often leading to complex and unusual distributions of stellar populations. In some cases, the interaction between a black hole and the stars can be so intense that high-velocity stars are ejected from the galaxy entirely, a phenomenon that speaks to the chaotic and sometimes violent nature of galactic centers. These high-speed stars, flung into intergalactic space, serve as a reminder of the raw power and unpredictability of these cosmic giants. The origins of supermassive black holes are still a subject of intense research and debate. While we have a solid understanding of their effects on galaxies, the question of how they form and grow remains one of the most compelling mysteries in modern astrophysics. One prevailing theory suggests that supermassive black holes may begin as smaller black holes, formed from the collapse of massive stars or the merging of smaller black holes. Over time, these black holes can grow by accreting gas and dust from their surroundings, as well as through mergers with other black holes. This growth process, it is believed, occurs in parallel with the evolution of the galaxy itself, reinforcing the idea that the fate of a galaxy and its supermassive black hole are deeply intertwined. Ultimately, the interplay between galaxies and their central supermassive black holes is one of the most intriguing aspects of the universe's evolution. These cosmic giants not only serve as the anchors around which galaxies form and develop, but they also play a decisive role in shaping the very structure and behavior of their host galaxies. As we continue to study these enigmatic forces, we are uncovering new and exciting insights into the fundamental workings of the cosmos, deepening our understanding of the forces that govern the universe at its most fundamental level. The Milky Way, our majestic and expansive galactic home, is not just a collection of stars and cosmic material. It is a stunning example of the vast, intricate design that underpins the universe itself. Starting from the very heart of our galaxy, the structure reveals an extraordinary architecture, with each component playing a vital role in the overall cosmic system. The core of the Milky Way houses a supermassive black hole, Sagittarius A, an unseen yet powerful force at the center of it all. Around this black hole lies a dense, spherical bulge packed with stars, many of which are among the oldest in the galaxy. This bulge serves as a testament to the Milky Way's deep and ancient origins, offering a glimpse into the processes that have shaped our cosmic home. In addition to the core, the galaxy's disk stretches out in a flat, rotating plane. Spanning nearly 100,000 light-years in diameter, this disk is a mix of stars, planets, gas, and dust. But it is far from uniform. Instead, it is punctuated by elegant, spiraling arms, each a region of intense cosmic activity. These arms, such as the Perseus and Sagittarius arms, are believed to be shaped by density waves, which compress gas and dust, creating a fertile ground for the formation of new stars. It's within this grand disk that our Sun resides, positioned in the Orion Spur, about 27,000 light-years from the galactic center. From this vantage point, we are granted a rare and precious view of the Milky Way's sprawling structure. However, much of our galaxy remains obscured by the interstellar dust and gas that permeate the space between the stars. Surrounding this galactic disk and bulge is a vast spherical halo, an immense cloud of stars and globular clusters that orbit the galactic core. These clusters, tight groups of stars that are remnants from the Milky Way's earliest days, offer crucial insights into the galaxy's formation and development. But the halo isn't just a relic of the past. It's also home to the majority of the galaxy's dark matter, the invisible, enigmatic substance that provides the unseen gravitational force necessary to keep the galaxy together. This dark matter not only influences the movement of stars and gas, but plays a fundamental role in maintaining the galaxy's structure. Beyond the Milky Way's immediate borders, a complex system of satellite galaxies also exists. These smaller galaxies, including the Large and Small Magellanic Clouds, are visible from Earth's southern hemisphere and are engaged in a delicate gravitational dance with our galaxy. Over billions of years, this interaction has shaped and will continue to shape the structure of these smaller galaxies. In time, it's believed that they may merge with the Milky Way, further enriching its vastness. The history of the Milky Way, its age, and the events that have unfolded within it are awe-inspiring. Scientists, through the diligent work of astronomers and astrophysicists, have determined that the Milky Way is approximately 6 billion years old, an age that places its formation just shortly after the Big Bang, which occurred about 13.8 billion years ago. This makes the Milky Way one of the oldest galaxies in the universe, offering us a direct link to the distant past of the cosmos. To calculate this age, scientists rely on a combination of observational techniques. One of the primary methods involves studying the oldest stars within the galaxy, particularly those in the halo and in globular clusters. These stars, rich in ancient history, have fewer heavy elements, as the heavier elements in the galaxy were formed in the cores of earlier generations of stars and dispersed through space when these stars died. By analyzing the abundance of elements in these ancient stars, scientists can estimate their age and, by extension, the age of the galaxy. Another way to gauge the galaxy's age comes from the study of the universe itself. By observing the cosmic microwave background radiation, the faint afterglow of the Big Bang, and measuring the rate at which the universe is expanding, scientists can calculate the age of the universe. Comparing this with the age of the oldest stars within the Milky Way confirms that our galaxy is among the earliest to form in the cosmos. Understanding the age of the Milky Way is more than just a matter of knowing how old it is. It provides crucial insights into the processes that led to the formation of galaxies and how they evolve over billions of years. The Milky Way's age reveals not only the longevity of our galaxy, but also the ancient forces that have shaped it. From the birth of the first stars to the intricate cosmic dance that continues to unfold across the galaxy's vast expanse. But what if we could peer back to the very beginning, to the moment when the universe began to take shape? The Milky Way, like the rest of the cosmos, was born in the aftermath of the Big Bang, and its story stretches across billions of years. Initially, it was a vast and formless cloud of gas and dust, slowly coming together in the early stages of cosmic evolution. As the universe expanded and cooled, this cloud began to collapse under the force of gravity, initiating a long, gradual process of formation. Over time, stars began to ignite from the gas, forming the first building blocks of galaxies. In the case of the Milky Way, this cosmic assembly was aided by dark matter, that invisible, mysterious substance that makes up a significant portion of the galaxy's mass. Its gravitational influence has played a crucial role in shaping the spiral structure we see today. The Milky Way, in many ways, acts as a snapshot of the larger universe, providing us with a window into the history of cosmic evolution. Understanding the age of our galaxy allows us to place astronomical events within the broader context of time. For example, the Sun, which formed around 4.6 billion years ago, is a relatively young star in comparison to the galaxy's core. This highlights the ongoing nature of star formation in the Milky Way, a continuous process that drives the dynamic evolution of our galaxy. The Milky Way isn't static. It's constantly evolving as new stars are born and old stars fade into oblivion, enriching the interstellar medium with elements essential for future generations of stars. At the very heart of this vast cosmic structure lies the galactic center, an area dense with activity and shrouded in mystery. Located approximately 27,000 light-years from Earth, the galactic center is home to Sagittarius A, SGRA, the supermassive black hole at the core of the Milky Way. With a mass 4 million times that of the Sun, SGRA is the anchor around which the entire galaxy revolves. Despite its relatively small size compared to the vastness of the Milky Way, this black hole exerts an enormous gravitational pull, dictating the orbits of nearby stars and gas clouds. The area surrounding this black hole is a hotbed of astronomical phenomena, from swirling gas clouds to bursts of high-energy radiation, all contributing to a dynamic and ever-changing environment. In this region, we find stars in a variety of stages of life. There are young, hot blue stars that burn with a fierce intensity, as well as older, cooler stars that have been in orbit around the galactic center for billions of years. The coexistence of these stars in such close proximity to a supermassive black hole raises intriguing questions for astronomers. The tidal forces near SGRA are immense, capable of ripping apart any gas clouds that venture too close. Yet the fact that new stars continue to form in this region suggests that there are unique, perhaps previously unknown, star formation processes at play here. It's as if the laws of astrophysics behave differently near the black hole. Beyond the stars, the galactic center is a region teeming with cosmic material. Vast clouds of gas and dust swirl around SGRA, some of which are slowly being consumed by the black hole, while others are in the process of forming new stars. Filaments of magnetic energy crisscross this area, and the intense radiation from the black hole's accretion disk creates an environment that is both hostile and fascinating. This region serves as an astrophysical laboratory where astronomers study the extreme conditions surrounding a supermassive black hole. Here, in this violent, high-energy environment, we witness phenomena such as X-ray flares and bursts of radiation, clues that help us understand the physics of black holes and the mysteries of energy transfer in some of the most extreme environments in the universe. Observing the galactic center is a difficult task, not least because of the dense clouds of interstellar dust that obscure our view. These dust clouds prevent us from seeing the galactic center in visible light, making it invisible to traditional telescopes. However, astronomers have found ways to pierce this veil of dust, using powerful radio, infrared, and X-ray telescopes to study the region. These observations have not only confirmed the existence of SGRA, but have also revealed a great deal about the black hole's properties and the energetic phenomena that occur in its vicinity. Thanks to these advances in technology, we've been able to gather insights into the behavior of the galaxy's core and the supermassive black hole that lies at its heart. But the Milky Way is not alone in its journey through the cosmos. It is part of a larger group of galaxies, bound together by the invisible force of gravity. The Milky Way has several smaller satellite galaxies that orbit around it, each with its own unique characteristics. Among the most well-known of these are the Large and Small Magellanic Clouds, two dwarf galaxies that are easily visible from the southern hemisphere. These galaxies, rich in gas and dust, are in close gravitational interaction with the Milky Way, and their interactions have shaped the structure of our galaxy over time. Far from being passive observers, these satellite galaxies actively influence the Milky Way, and their gravitational dance has profound implications for the future of both galaxies. In fact, the Milky Way's interactions with its satellite galaxies are far from harmonious. The gravitational pull between them is not always gentle. At times, these interactions can lead to cosmic collisions, where the galaxies merge or have stars stripped away. These events play a critical role in the ongoing evolution of the Milky Way and its smaller companions, impacting everything from their star formation rates to the distribution of dark matter. Ultimately, the Milky Way's relationships with these satellite galaxies are a testament to the dynamic, ever-changing nature of the universe. The universe is not a static place, and neither is our galaxy. As the Milky Way continues to evolve, we are left to wonder what the future holds for this vast, interconnected web of galaxies and cosmic forces. As the Milky Way orbits the vast expanse of the cosmos, gravitational forces between it and nearby celestial bodies like the Magellanic Clouds play a pivotal role in shaping its evolution. These invisible forces drive an array of dynamic phenomena, most notably tidal stripping, where gas is drawn away from the smaller satellite galaxies. This material, once stripped, can be funneled into the Milky Way, enriching its gas reservoir and fueling the formation of new stars. However, the gravitational dance between these galaxies isn't a one-sided affair. The Magellanic Clouds, while being influenced by the Milky Way, also exert their own pull on our galaxy, causing subtle but significant distortions. For instance, their gravitational effect has been instrumental in warping the Milky Way's disk, a phenomenon that provides a tangible reminder of the interconnectedness of galaxies. These interactions, far from being passive, actively shape the structure of the galaxies involved. In particular, the Magellanic Clouds have given rise to spectacular tidal streams, long, winding trails of stars and gas that have been stripped from smaller galaxies. Some of these streams have their origins in long-lost galaxies now fully consumed by the Milky Way, offering us invaluable glimpses into the galaxy's distant past and its evolving relationship with its satellite galaxies. The Sagittarius dwarf spheroidal galaxy provides another striking example of this cosmic interplay. Once a distinct galaxy, it is now in the throes of being devoured by the Milky Way. As it is torn apart by the gravitational forces of our galaxy, the remnants of this celestial merger can be seen as stellar streams that wrap around the Milky Way like a cosmic ribbon. These streams and their delicate tracings offer a testament to the forces of galactic evolution and provide clues to the fates of countless satellite galaxies that will eventually meet similar ends. Such mergers are far from random occurrences or catastrophic events. They are fundamental processes in the ongoing evolution of galaxies. The assimilation of smaller galaxies provides the Milky Way with fresh supplies of gas, which in turn fuels new generations of stars and adds complexity to the galaxy's chemical makeup. These mergers also redistribute matter throughout the galaxy, influencing its overall structure and the dynamics of its stars, planets, and other cosmic inhabitants. Looking forward, the future of the Milky Way promises even more dramatic changes, as gravitational forces, star formation, and galaxy mergers continue to reshape the galaxy's destiny. In the not-so-distant future, astronomically speaking, the Milky Way is predicted to undergo one of the most significant transformations in its history, its collision with the Andromeda Galaxy. Currently, Andromeda is a mere 2.5 million light-years away and hurtling towards us at an impressive 110 kilometers per second. In roughly 4 billion years, this grand cosmic merger will begin, and the skies above Earth, or any planet fortunate enough to have observers by then, will bear witness to one of the universe's most spectacular events. As the Milky Way and Andromeda draw closer, under the weight of their mutual gravitational attraction, they will ultimately collide and merge into a single larger elliptical galaxy. This new, combined galaxy is often affectionately referred to as Milkomeda, or Milky-Dromeda in scientific discussions. Interestingly, this merger is not expected to be a cataclysmic event. Due to the vast spaces between individual stars, direct star-to-star collisions are incredibly unlikely. Instead, this merger will unfold as a complex dance of stellar orbits, with stars and planetary systems being flung into new paths, some possibly even ejected from the newly formed galaxy altogether. The gas clouds within both galaxies, however, will collide violently, triggering an intense burst of star formation. New stellar nurseries will light up the newly formed galaxy, adding even more stars to its already stunning population. In the aftermath of the merger, the center of the new galaxy will be dominated by the combined masses of the Milky Way's and Andromeda's supermassive black holes. Over millions of years, these two black holes will spiral toward each other, eventually merging in an event that will release enormous amounts of energy. This cosmic spectacle will send ripples through the fabric of space-time itself, manifesting as gravitational waves that can be detected across vast distances. Beyond this galactic collision, the long-term future of the Milky Way will be shaped by the natural life cycles of its stars. As stars exhaust their nuclear fuel, they will evolve, with massive stars exploding in dramatic supernova, while smaller stars shed their outer layers, creating planetary nebula. Over the course of trillions of years, this stellar evolution will leave the Milky Way populated by dim white dwarfs, neutron stars, and black holes. Moreover, the ongoing expansion of the universe will influence the Milky Way's future. As distant galaxies continue to recede beyond our observational reach, the universe will appear increasingly empty from our vantage point. However, the gravitational bonds that tie the Milky Way to its local group of galaxies will preserve this cosmic enclave. In an ever-expanding universe, the Milky Way and its neighbors will form a small oasis of matter, standing resilient as the universe around them grows increasingly desolate. The story of the Milky Way, its interactions, mergers, star formations, and eventual fate, is a testament to the ever-changing dynamic nature of the cosmos. Through the lens of time, we see that our galaxy is far from static. Rather, it is an ever-evolving entity, shaped by the forces of gravity, star formation, and cosmic collisions, all woven together in the grand tapestry of the universe's evolution. The formation of the solar system is a fascinating tale, one that spans billions of years and takes us back to the very origins of our cosmic neighborhood. This journey began approximately 4.6 billion years ago when a cloud of gas and dust in the Milky Way, known as the Solar Nebula, began its slow collapse under the weight of its own gravity. But it wasn't just the force of gravity at play. A nearby supernova likely triggered this collapse, sending a shockwave through the nebula, adding energy and causing it to compress even further. As this cloud of material began to collapse, it began to spin, flattening into a rotating disk with the densest material gathering at the center. At the heart of this swirling disk, a protostar began to form, a baby star that would eventually ignite and become the sun. The process was one of transformation. Hydrogen atoms fused together, creating nuclear reactions that released vast amounts of energy, heating the core and marking the beginning of our sun's life. Around this newborn star, the remaining material in the disk slowly began to clump together. As particles collided and stuck to each other, they grew into larger bodies. This gradual accumulation of material, called accretion, was the birth of the planets. In the regions closest to the sun, temperatures were scorching hot, which allowed metals and silicates to condense. Here, rocky planets like Mercury, Venus, Earth, and Mars took shape. These planets were dense, composed mainly of silicate rocks and metals, and Earth was the only one among them to develop an atmosphere and sustain life as we know it. Farther out, beyond what is known as the frost line, temperatures dropped dramatically, allowing water, ammonia, and methane to freeze. This colder region gave rise to the gas giants and ice giants. Jupiter and Saturn, the gas giants, amassed huge amounts of hydrogen and helium, swelling to immense sizes, while Uranus and Neptune, the ice giants, gathered their mass from water and methane ices. These two groups of planets, though distinct, were shaped by the same forces of accretion, but in different ways due to their positions relative to the sun. Beyond the planets, the outermost regions of the solar system are home to the Kuiper Belt and the Oort cloud. These distant regions contain countless icy bodies, comets, and dwarf planets like Pluto. These objects are remnants from the early solar system, fossils of a time when the solar system was still forming. They have remained largely unchanged since their creation, offering scientists a direct glimpse into the conditions that existed long ago. One of the most intriguing elements of the solar system's formation story is the role of Jupiter. As the largest planet in the system, Jupiter's immense gravity had a profound impact on the evolution of the solar system. It influenced the orbits of many other bodies, shaping the architecture of the solar system. It also likely caused some objects to be flung into the sun or cast out into the far reaches of space. Jupiter's gravitational influence continues to affect the motion of objects in the outer solar system today, and its presence may have even helped prevent the inner planets from being bombarded by excessive amounts of space debris. Throughout the solar system's history, it has experienced dramatic changes, shaped by collisions, migrations, and other dynamic events. The late heavy bombardment, which took place around 3.8 billion years ago, was a period of intense comet and asteroid impacts that left their marks on the planets. These impacts not only shaped the surfaces of the planets, but also played a crucial role in the development of life on Earth, as some scientists believe that these impacts brought water and other essential chemicals to our planet. Today, scientists rely on a combination of observational data, computer simulations, and the study of meteorites to piece together the story of the solar system's formation. These methods allow researchers to examine the chemical composition of ancient materials and study the processes that led to the creation of the planets. Through this work, we not only uncover the origins of our own solar system, but also gain insights into how other planetary systems may have formed elsewhere in the galaxy. The Milky Way, our home galaxy, played an essential role in the birth of the solar system. The vast clouds of gas and dust within the Milky Way, along with its gravitational forces, set the stage for the collapse of the solar nebula. The life cycles of stars in the galaxy, including supernova, seeded the interstellar medium with heavy elements that would later form planets and other cosmic bodies. Without the Milky Way's influence, the conditions necessary for the formation of the solar system would not have existed. At the core of this cosmic tale lies the interstellar medium of the Milky Way, a mix of hydrogen, helium, and dust particles, each of which played a crucial role in the development of the Sun, planets, moons, asteroids, and comets. As we continue to explore the farthest reaches of the solar system, we are reminded that our cosmic story is just one chapter in the ongoing saga of the universe. Every discovery, whether through a telescope or a meteorite sample, brings us closer to understanding the forces and events that shaped the solar system, and by extension, our own place in the cosmos. And so, the story of our solar system begins in the vast depths of the Milky Way galaxy. Over billions of years, it was a region of unimaginable turmoil and transformation, where the remnants of long-dead stars gave birth to the very elements essential for life. These heavy elements, carbon, oxygen, and iron, were forged in the explosive deaths of massive stars, known as supernovae. Through this dramatic process, the galaxy was seeded with the building blocks of planets, and ultimately, life. Within this swirling galaxy, the Milky Way's spiral arms played an instrumental role in shaping the fate of the solar system. The gravitational forces within these arms triggered the birth of new stars, sweeping through the interstellar medium, compressing gas and dust, and igniting the formation of stellar nurseries. It was in such a dynamic, ever-evolving environment that our solar system took root. Nestled within a dense region of a molecular cloud, the conditions were ideal for the solar nebula, the vast cloud of gas and dust that would eventually collapse under its own gravity, giving birth to the sun and the planets. This cosmic setting was not only fertile in terms of the elements present, but also in the unique chemical composition that marked the history of the Milky Way. The specific mixture of elements in the region where our solar system formed played a pivotal role in determining the kinds of planets that would emerge. The inner planets, Mercury, Venus, Earth, and Mars, formed from materials that could condense at the high temperatures near the young sun. Meanwhile, further out in the cooler regions of the solar system, the gas giants and ice giants began to take shape, gathering volatile compounds that would later form their massive atmospheres. The solar system's location within the Milky Way was also critical. Positioned in the Orion Arm, A quiet region nestled between the galactic arms, the solar system avoided the chaotic forces at the galactic center. It was spared the intense radiation and gravitational disturbances that might have destroyed planets and planetary systems closer to the bustling heart of the galaxy. This unique, relatively stable environment has allowed life to thrive on Earth, offering us a peaceful vantage point to observe the galaxy's wonders and its complex evolution. As we look back at the formation of Earth, it is a tale that spans over 4.6 billion years, unfolding within the swirling disk of gas and dust known as the solar nebula. This era, guided by the unyielding laws of physics, saw the birth of our planet within the cradle of the early solar system. As the nebula collapsed under its own gravity, it spun rapidly and flattened into a disk, with the sun beginning to form at the center. This new star ignited, casting out light and heat into the surrounding space. Far from the sun's warmth, in the cooler reaches of the disk, dust and ice particles began to collide, sticking together and gradually forming larger clumps. These clumps grew over time, evolving into planetesimals, the building blocks of the planets. These planetesimals, driven by their own gravity, collided and merged in a process known as accretion, forming the rocky cores of the inner planets, including Earth. In those early stages, Earth grew rapidly, gaining about 60% of its present size in just a few tens of millions of years. However, this growth came at a cost. The young Earth was bombarded by countless impacts, causing immense heat to build up within its interior. This heat, along with the decay of radioactive elements, caused the Earth to partially melt. As it did, the planet began to differentiate into distinct layers: a dense metallic core, a silicate mantle, and a crust. The formation of Earth's core was especially significant, for it was this core that would eventually generate the planet's magnetic field, a shield that protects the surface from the harmful effects of solar and cosmic radiation. Meanwhile, volcanic activity and intense heat from the planet's interior released gases that had been trapped within its rocks. These gases, including water vapor, carbon dioxide, methane, and ammonia, began to form the early atmosphere of Earth. Unlike the breathable air we know today, this primordial atmosphere was thick, heavy, and hostile to life. Yet it was this very atmosphere that laid the foundation for the conditions that would eventually allow life to take root and flourish. Thus, the stages of Earth's formation were not merely a matter of physical development. They were also a prelude to a much grander, interconnected narrative, the ongoing evolution of life, shaped by the forces of nature and the cosmic dance of the stars. Through the unfolding of these events, Earth became not just a planet, but a world uniquely suited to harbor life as we know it, a story etched in the very elements that birthed it. Water vapor in the early atmosphere of Earth, once released by volcanic activity, eventually condensed as the planet cooled, giving rise to rain. Over time, this rain filled the depressions on the planet's surface, forming vast basins. These basins gradually transformed into oceans, an essential element for life as we know it. This seemingly simple process of condensation and rainfall set the stage for the complex biological story that would unfold. As Earth's surface evolved, its size, orbit, and protective magnetic field created an environment perfectly suited for life. Earth's magnetic field, which arises from the movement of molten iron in its core, shields the planet from harmful solar and cosmic radiation. This protection allowed Earth's atmosphere to remain intact, offering a stable environment for life to emerge. These conditions, combined with the presence of liquid water, created the foundation upon which all life would build. Over billions of years, Earth's atmosphere and surface underwent dramatic changes. The planet's geological activity, from volcanic eruptions to the shifting of tectonic plates, continuously reshaped the landscape. Plate tectonics not only formed continents and ocean basins, but also played a critical role in regulating Earth's temperature and recycling carbon through the carbon silicate cycle. The interactions between Earth's geology and atmosphere have continued to create a dynamic environment that supports a diverse range of life forms. The emergence of life on Earth was a direct result of these interconnected processes. Life began as simple microorganisms, but the most transformative event was the rise of photosynthetic organisms. These early life forms, capable of harnessing sunlight to convert carbon dioxide and water into oxygen and glucose, slowly began to change Earth's atmosphere. Over millions of years, the accumulation of oxygen in the atmosphere not only made the environment more hospitable to a variety of organisms, but also led to the formation of the ozone layer, which protects life from harmful ultraviolet radiation. Earth's position in the solar system, often referred to as the Goldilocks zone, was another fundamental condition for life to thrive. Located at just the right distance from the sun, neither too hot nor too cold, Earth's orbit allowed liquid water to exist on its surface. Liquid water, essential for all life processes, became a defining feature of the planet, enabling the complex biochemical reactions that sustain living organisms. This delicate balance between distance from the sun and the presence of water created the perfect environment for life to begin and evolve. But the story of life on Earth was not just about location and physical conditions. It was also about the planet's atmosphere. Initially composed of gases like water vapor, carbon dioxide, and ammonia, Earth's atmosphere began to change over time. As photosynthetic organisms proliferated, they released oxygen into the atmosphere, gradually transforming it into the oxygen-rich environment we rely on today. This oxygenation of the atmosphere was a key factor in supporting more complex life forms and laid the groundwork for the development of animals and plants. Moreover, Earth's magnetic field further enhanced its suitability for life. Without this protective shield, the constant barrage of solar winds and cosmic radiation could have stripped away the atmosphere, leaving the planet inhospitable. Instead, Earth's magnetic field ensures the atmosphere remains intact, helping to maintain the planet's habitability. The role of water in shaping life on Earth cannot be overstated. Water exists on Earth in all three states, solid, liquid, and gas, and its versatility is critical for life. As a solvent, water facilitates chemical reactions essential for biological processes. Its unique properties, such as its ability to dissolve a wide range of substances, make it indispensable in the formation of complex biological molecules. From the simplest cells to the most advanced life forms, water plays a fundamental role in supporting life's complexity. In addition, Earth's natural satellite, the Moon, has been instrumental in stabilizing the planet's climate. By influencing the tilt of Earth's axis, the Moon has helped maintain a relatively stable climate over millions of years, allowing for the development of diverse ecosystems. Without this stability, Earth's climate would have fluctuated more dramatically, making it far more difficult for life to thrive. But while Earth was uniquely positioned to foster life, it was not alone in the vast expanse of the universe. In fact, dark energy, a mysterious force that remains largely unexplained, plays a significant role in the cosmos, influencing the universe's structure and fate. Though still a topic of much speculation and study, dark energy's effect on the expansion of the universe could have far-reaching implications for understanding our place in the cosmos. From the formation of oceans to the rise of life, from the protection provided by Earth's magnetic field to the stabilizing influence of the Moon, the conditions that make Earth a cradle for life are a complex interplay of cosmic and terrestrial forces. Over billions of years, these factors have shaped our planet, making it a living, dynamic world capable of sustaining life in all its forms. Understanding this delicate balance is crucial, as it allows us to appreciate the unique conditions that make Earth not just a planet, but a home to the most extraordinary variety of life in the known universe. This enigmatic force, known as dark energy, makes up about 68% of the universe. It is the mysterious power behind the accelerated expansion of the cosmos, a discovery that has revolutionized our understanding of the universe since its observation in the late 1990s. Initially, scientists expected that gravity would slow down the expansion of the universe over time, but the observation of distant supernovae revealed an astonishing truth. Galaxies are moving away from each other at an accelerating pace. This unexpected acceleration pointed to the presence of an unknown energy, an invisible force that permeates all of space. It exerts a repulsive force so powerful that it overcomes the gravitational pull that holds galaxies together. Since its discovery, dark energy has become one of the most profound mysteries in physics. Despite its vast influence on the universe's expansion, the true nature of dark energy remains elusive. However, Scientists have been able to study its impact by examining the way galaxies are spreading apart. Without dark energy, the universe might have collapsed under the force of gravity or expanded at a much slower rate, leading to a vastly different cosmic landscape. Dark energy is thus shaping the very structure of the universe, guiding the formation of galaxies and the evolution of cosmic structures. One of the most prominent theories about dark energy is the cosmological constant. Proposed by Albert Einstein as a modification to his theory of general relativity, the cosmological constant suggests that space itself is filled with a constant, unchanging energy density. This energy would have a fixed value that remains unaffected by the passage of time. On the other hand, another possibility is that dark energy could be a dynamic field, much like an electromagnetic field, with properties that vary across space and time. If this is the case, the rate of the universe's expansion could change over time, leading to new insights about the fate of the cosmos. As we look further into the future, the presence of dark energy raises intriguing questions about the ultimate destiny of the universe. If dark energy's density remains constant or increases, the universe will continue to expand indefinitely, growing colder and emptier as galaxies drift farther apart. Alternatively, if dark energy strengthens its repulsive force, it could lead to a big rip, where galaxies, stars, and even atoms are torn apart by the accelerating expansion. This vision of cosmic destruction would mark the end of the universe as we know it, an outcome that remains both fascinating and terrifying. The study of dark energy is crucial not just for cosmology, but also for fundamental physics. It challenges our current theories and could hold the key to unlocking new laws of nature. To unravel this mystery, scientists are using a range of methods, from studying the cosmic microwave background to observing galaxy distributions and supernovae. They are also conducting experiments that probe the very nature of space and energy, hoping to gain deeper insights into the forces shaping the universe. Meanwhile, the evolution of galaxies themselves adds another layer of complexity to our understanding of the cosmos. Galaxies are not static. They are dynamic systems that evolve over time. This process, unfolding over billions of years, is driven by a variety of cosmic forces, including the gravitational pull of other galaxies, interactions with intergalactic matter, and the continuous cycle of star birth and death. Understanding the evolution of galaxies is essential for uncovering the history of the universe, revealing the life cycle of the fundamental building blocks of the cosmos. In the early universe, shortly after the Big Bang, galaxies began as small, primordial structures known as proto-galaxies. Over time, these proto-galaxies merged and grew, accumulating gas and other matter. This process led to the diverse range of galaxy shapes and sizes that we observe today. From the spiral galaxies, like our own Milky Way, to the elliptical and irregular galaxies scattered across the universe, each galaxy's evolution is shaped by its mass, environment, and interactions with neighboring galaxies. For spiral galaxies, star formation plays a central role in their ongoing evolution. The spiral arms, rich in gas and dust, are active regions where new stars are born from the gravitational collapse of gas clouds. However, as these galaxies age, they begin to exhaust their gas supplies. The rate of star formation decreases as the interstellar gas is consumed, either by new star births or ejected into space during supernova explosions. This process eventually leads to the transformation of a once vibrant star-forming galaxy into a more stable, older structure, altering its appearance and character over time. As dark energy continues to shape the cosmos, its effects ripple through the evolution of galaxies, influencing the trajectory of the universe's growth and development. The interplay between dark energy, gravity, and the matter that makes up galaxies creates a complex and ever-changing cosmic dance. With each discovery, we come closer to unraveling the mysteries of the universe, yet the full story of dark energy and the fate of our cosmos remains far from complete. The journey to understand the nature of the universe is only beginning, and each new revelation opens the door to even greater questions about the origins and destiny of all that exists. But over time, galaxies evolve, and their stellar populations age. As stars burn through their fuel, older, redder stars begin to dominate the galaxy's appearance, especially in spiral galaxies. This gradual aging process can make galaxies appear more mature, and the result is often a population of stars that are dimmer and older. However, in elliptical galaxies, the process of evolution takes a different path, particularly due to the violent cosmic events that shape them. These galaxies often emerge from the mergers of smaller galaxies, and the resulting chaos can be both destructive and transformative. Mergers are powerful events, compressing gas clouds and triggering starbursts, yet these same processes often scatter and heat the gas, making it less likely to form new stars. As a result, elliptical galaxies tend to have older, redder stars and lack the abundant interstellar gas seen in spiral galaxies. While star formation may have been triggered in the initial moments of a merger, these events often leave a lasting impact, depleting the galaxy's gas supply and inhibiting future stellar birth. This paints a picture of the harsh realities of galactic evolution, a continuous battle between creation and destruction, with the balance of gas and stars shifting over time. Galaxy interactions, particularly mergers and close encounters, drive much of this evolution. These events disrupt a galaxy's structure, changing its shape and triggering bursts of star formation. For example, when two similarly sized galaxies collide, the result can be the formation of a much larger elliptical galaxy. This collision often obliterates the spiral structure of the original galaxies, making way for a smoother, more rounded formation. In addition, gravitational interactions with neighboring galaxies can distort the shape of a galaxy, leading to the creation of tidal tails, bridges, and other striking features. These dramatic alterations in shape and star formation are some of the most profound aspects of galactic evolution, painting a picture of how galaxies are constantly being reshaped by the gravitational forces around them. Beyond external forces, internal processes also influence a galaxy's development. One such process is feedback from supernovae, which inject energy into the surrounding interstellar medium. This energy heats the gas and expels it from the galaxy, reducing the amount of material available for new star formation. Similarly, active galactic nuclei, AGN, powered by supermassive black holes at the centers of galaxies, can expel vast amounts of gas and dust, further hindering the galaxy's ability to produce stars. Over time, the combination of these internal and external forces causes galaxies to age. Star formation rates decline, and the stellar population becomes progressively older and redder. The environment of a galaxy plays a significant role in this process. Galaxies located in denser regions, such as the centers of galaxy clusters, evolve faster due to more frequent interactions and the stripping of gas by the hot intracluster medium. The role of galaxy collisions in cosmic evolution cannot be overstated. These cataclysmic events, which unfold over hundreds of millions of years, are central to shaping the universe as we know it. They are more than just spectacular cosmic phenomena. They are fundamental to the evolution of galaxies and the shaping of the very structure of the universe. When galaxies collide, gravitational forces between them create an intricate web of interactions that can change the very fabric of the galaxies involved. This complex dance of forces can lead to dramatic transformations, including the birth of new stars and the creation of entirely new types of galaxies. Despite the enormous distances between stars within a galaxy, the immense gravitational forces at play during a collision can redistribute gas, dust, and stars, leading to the formation of fascinating structures like tidal tails, rings, and bridges. One of the most significant results of these collisions is the triggering of starburst events. As the interstellar gas clouds within the merging galaxies are compressed, new stars are born at an accelerated rate. These starbursts can generate millions of new stars over a relatively short time, dramatically changing the galaxy's composition and appearance. This process plays a vital role in the life cycle of galaxies and in the distribution of elements necessary for life. The new stars formed in these starbursts will eventually produce heavier elements in their cores, enriching the interstellar medium and providing the building blocks for future generations of stars, planets, and even life itself. Moreover, galaxy collisions can also result in the formation of supermassive black holes at the centers of galaxies. When galaxies merge, their central black holes are drawn closer together, eventually colliding and merging as well. This process releases enormous amounts of energy, which can influence the surrounding galaxy, potentially regulating star formation and shaping the galaxy's future. Many astronomers believe that elliptical galaxies, which lack the defining spiral arms of their spiral counterparts, are the result of such mergers. The collision and mixing of stars and gas from two spiral galaxies produce the more uniform and featureless appearance of elliptical galaxies. In this sense, mergers serve as a crucial process in the ongoing evolution of galaxies, mixing and redistributing the components of the original systems to create entirely new structures. At a broader level, galaxy collisions and mergers are central to the hierarchical model of galaxy formation. This theory proposes that galaxies form and evolve through the accumulation of smaller systems, a process that has been ongoing since the early days of the universe. The collisions and mergers of galaxies continue to shape the large-scale structure of the cosmos, affecting the distribution of galaxies within clusters and superclusters, and driving the ever-evolving landscape of the universe. The significance of galaxy collisions goes far beyond the immediate, often violent changes they bring. These cosmic clashes serve as a profound reminder of the universe's dynamic and ever-evolving nature. As massive galaxies collide, they reveal critical insights about the processes that drive cosmic evolution, the enigmatic behavior of dark matter, and the gravitational forces that shape the cosmos itself. Observing and simulating these collisions is not just about understanding our past and present, but also about peering into the vast unknowns of our universe's future. Our very own Milky Way is on a collision course with the Andromeda Galaxy, an event that promises to be a spectacular merger happening in approximately 4 billion years. But what does this collision tell us about the grander future of the universe? Predicting the ultimate fate of the cosmos is a challenge that has captured the imagination of astronomers and cosmologists for centuries. By blending observations, theoretical physics, and computer simulations, scientists have crafted theories that allow us to glimpse into the distant future of the universe. Yet, even with our current understanding of dark energy, dark matter, and gravity, certainty remains elusive. A key player in these predictions is dark energy, the mysterious force pushing the universe's expansion at an accelerating rate. If this force continues its dominance, it will likely lead the universe into a future scenario known as the Big Freeze, or heat death. In this cold, distant future, galaxies will drift farther apart, with star formation gradually ceasing as galaxies deplete their gas reserves. Over trillions of years, the stars that remain will burn out, leaving behind remnants like white dwarfs, neutron stars, and black holes. Even these remnants won't last forever. Eventually, they may be consumed by black holes. And through a process known as Hawking radiation, even black holes themselves will slowly evaporate. As time stretches on, the universe will grow darker and colder, fading into an eternal empty void. However, there is another possibility for the universe's future, one that hinges on the unpredictable nature of dark energy. If dark energy intensifies over time, its repulsive force could become so overpowering that it would tear the very fabric of reality apart, in a cataclysmic event known as the Big Rip. In this future, galaxies, stars, planets, and eventually even atoms would be pulled apart by the force of dark energy. The universe would meet its end in an explosive, destructive finale that leaves nothing behind. Alternatively, if the universe contains enough matter, both visible and invisible, including dark matter, it could eventually overcome the force of dark energy. This could trigger a reverse in the universe's expansion, leading to a process known as the Big Crunch. In this scenario, the universe would collapse in on itself, mirroring the conditions of the Big Bang, potentially creating the conditions for a new universe to emerge from the ashes of the old one. The Big Bounce theory suggests that the universe could follow a cyclical pattern, repeatedly expanding and contracting in an endless loop of creation and destruction. As we continue to explore these possibilities, it's important to remember that these theories are based on our current understanding of cosmology. While we have made tremendous strides in understanding the forces that govern the universe, the true fate of the cosmos is still uncertain. New observations, particularly in the realms of dark energy and dark matter, may lead to new insights that challenge or refine these predictions. Nonetheless, these theories serve to remind us of the universe's ever-changing nature, offering a glimpse into the profound and awe-inspiring questions that fuel the field of cosmology. The future of the universe is far from settled, and as our understanding grows, so too will our ability to peer further into the depths of time. Venturing into the vast expanse of the universe, astronomers employ an array of sophisticated techniques, each designed to peel back the layers of cosmic mystery and bring us closer to understanding the very fabric of existence. This celestial exploration goes far beyond the simple telescopes one might imagine sitting in an amateur astronomer's backyard. At the forefront of this monumental endeavor are colossal instruments of immense power, equipped with cutting-edge technology. These titanic telescopes are stationed around the globe, and some even venture beyond the Earth's atmosphere to capture the faintest whispers of light from distant galaxies and stars, light that has traveled for billions of years to reach us. The light we receive from these distant celestial bodies is not just a flicker in the dark. It is a message from the cosmos, a bearer of secrets that could unlock the mysteries of the universe. By analyzing this light, scientists can uncover not only the composition of faraway stars and galaxies, but also their distance from us, their age, and even their velocity in the great cosmic dance that continues to unfold. The technique that makes this possible is called spectroscopy, a process that splits light into its component colors, much like a prism turning sunlight into a rainbow. Each color corresponds to a specific wavelength, and each wavelength is a clue that tells astronomers what elements make up the celestial objects they study. This method of analyzing light goes beyond just identifying what stars and galaxies are made of. It also reveals their motion through the universe. When light from a distant object shifts toward the red end of the spectrum, this is known as redshift, and it signifies that the object is moving away from us. Conversely, a shift toward the blue end of the spectrum, or blue shift, indicates an object moving toward us. These shifts, caused by the Doppler effect, are not just fascinating quirks of physics. They hold the key to understanding the very nature of the universe. In fact, it was the discovery of redshift in the light from distant galaxies that led to the revolutionary theory of an expanding universe, a cornerstone of modern cosmology. As technology continues to advance, our ability to peer further into the cosmos grows exponentially. The Hubble Space Telescope, now orbiting the Earth, has sent back images of unparalleled clarity, unveiling the intricate structures of distant galaxies and nebulae. However, Hubble is only the beginning. Its successor, the James Webb Space Telescope, was specifically designed to look even deeper into the universe. Webb's mission is to observe the very first galaxies that formed after the Big Bang, shedding light on a time long before the birth of stars and planets as we know them. These space-based observatories offer a crucial advantage. They are free from the distortions caused by Earth's atmosphere, which can blur and obscure the view of even the most advanced ground-based telescopes. With this newfound clarity, astronomers can see more detail than ever before, unraveling cosmic secrets that have remained hidden for eons. Yet, space-based telescopes are not the only tools in the astronomer's arsenal. Radio telescopes, which listen to the universe's whispers in radio waves, provide an entirely different perspective on the cosmos. These colossal dishes capture radio emissions from celestial objects, offering insights into phenomena that optical telescopes cannot detect. For instance, radio telescopes are capable of detecting the faint glow of cosmic microwave background radiation, the afterglow of the Big Bang itself, providing invaluable information about the universe's earliest moments. Together, optical and radio telescopes create a more comprehensive understanding of the universe. But astronomers don't stop there. The integration of observations from telescopes across the entire electromagnetic spectrum, from radio waves to gamma rays, has opened the door to groundbreaking discoveries. This multi-wavelength approach has allowed scientists to detect phenomena such as quasars and pulsars, objects so extreme they challenge the limits of our understanding, yet offer profound insights into the ongoing evolution of the cosmos. In the pursuit of greater cosmic clarity, astronomers rely on a range of technologies that enhance the power of telescopes and help them delve deeper into the mysteries of the universe. Among these, adaptive optics has proven to be a game changer for ground-based astronomy. This technology, which compensates for the blurring effects of Earth's atmosphere, allows telescopes to capture images with a level of clarity once thought impossible from the surface of our planet. By using a reference star or a laser guide star to measure atmospheric distortions, adaptive optics systems adjust the telescope's optics in real time, correcting for the blurring caused by turbulence in the air. This breakthrough enables astronomers to observe distant galaxies and other celestial objects with unprecedented precision, offering clearer views than ever before. Another critical tool in the quest to understand the universe is interferometry. This technique involves the combination of light from multiple telescopes, effectively creating a single, highly detailed image. By linking several observatories, interferometry overcomes the limitations of individual telescopes, providing astronomers with a level of resolution that surpasses the capability of any one instrument alone. This collaborative approach is revolutionizing our ability to observe the cosmos, offering a more complete and detailed picture of distant stars, galaxies, and other cosmic phenomena. Together, these advancements in technology, from adaptive optics to interferometry, are pushing the boundaries of what we can observe in the universe. As we continue to develop more sophisticated tools and techniques, the mysteries of the cosmos become ever more accessible, bringing us one step closer to understanding the vast and awe-inspiring universe in which we live. But what if the very way we look at the universe could be transformed, allowing us to peer into the farthest reaches of space with an unprecedented clarity? This is the power of interferometry, a groundbreaking technique that merges the power of multiple telescopes to create a virtual telescope as large as the distance between them. Such an advancement enhances the resolution of astronomical images in ways that were once unimaginable, allowing us to observe distant cosmic phenomena with stunning precision. In Chile, the Very Large Telescope, VLT, and the Atacama Large Millimeter Submillimeter Array, ALMA, stand as prime examples of this technology at work. With the combined strength of their individual telescopes, these observatories give us a closer look at the processes of star formation, the birth of planetary systems, and the intricate structure of galaxies light years away. These techniques provide an unparalleled level of detail that once seemed out of reach, shedding light on phenomena such as black holes, the remnants of ancient stars, and the elusive dark matter. Meanwhile, radio astronomy remains a cornerstone of our cosmic exploration, offering a powerful tool that optical telescopes simply cannot. Unlike optical telescopes that capture visible light, radio telescopes are designed to detect radio waves emitted by celestial objects, enabling us to explore the universe's unseen realms. This unique ability is crucial for observing phenomena like the cosmic microwave background radiation, the faint echo of the Big Bang, as well as the mysterious fast radio bursts that originate from deep within space. The Square Kilometer Array, a monumental international collaboration, is set to build the world's largest radio telescope. With its vast network of antennas, it promises to uncover the universe's earliest moments, map galaxy distributions, and answer profound questions about the origins of cosmic structures. Beyond the Earth's surface, space missions and satellites continue to deepen our understanding of the galaxy. Instruments like the Gaia Observatory are revolutionizing our knowledge by mapping the positions and movements of billions of stars within the Milky Way. This data is crucial for deciphering the galaxy's formation and evolution. Similarly, missions like Kepler and the Transiting Exoplanet Survey Satellite, TESS, have significantly advanced our search for exoplanets, planets orbiting stars beyond our solar system. Their discoveries spark new questions about the potential for life on other worlds, offering tantalizing possibilities for humanity's future in the cosmos. The explosion of data produced by these observatories necessitates the growing field of computational astronomy. With sophisticated algorithms and powerful computer models, astronomers can simulate the complex phenomena of the universe, from black hole dynamics to the formation of galaxies. These tools have transformed theoretical physics, allowing scientists to test ideas about the cosmos that were once thought impossible to verify. By applying these computational techniques, astronomers can investigate the formation of stars and galaxies, the behavior of supermassive black holes, and the very fabric of space-time itself. And when we look at the technology behind these advancements, it becomes clear that telescopes are at the heart of our quest for understanding. These ingenious instruments serve as the eyes of humanity, extending our vision far beyond the Earth's atmosphere to reveal the wonders of the universe. At their core, telescopes are designed to gather and magnify the light emitted by distant stars, galaxies, and other celestial objects, transforming them from distant pinpricks of light into detailed images that reveal the secrets of the cosmos. The principles of telescopes are rooted in the science of optics, the study of light. Two primary types of telescopes serve astronomers: refracting and reflecting. Refracting telescopes use lenses to bend or refract light. When light from a distant star enters the telescope, it passes through the objective lens, where it is focused at a single point, the focal point. By magnifying the light at this point, the image becomes visible through an eyepiece. The larger the objective lens, the more light it can capture, and the clearer the faintest objects become. Reflecting telescopes, however, use mirrors to gather and focus light. A large curved primary mirror collects the light and directs it to a focal point. Before the light reaches the focal point, it is redirected by a secondary mirror, which sends the light to an eyepiece or detector. Reflecting telescopes have a distinct advantage in that they avoid chromatic aberration, a problem in refracting telescopes where different colors of light are bent by different amounts, causing color distortions. As technology progresses, modern telescopes incorporate cutting-edge technologies like adaptive optics. Adaptive optics correct for the blurring caused by the Earth's atmosphere, enabling astronomers to capture clearer images. By rapidly adjusting the shape of the telescope's mirror in real time, astronomers can counteract the distortions in the atmosphere, resulting in sharp, crisp images of distant celestial bodies. These technological innovations, combined with the increasing size of mirrors, have enabled telescopes to achieve resolutions that were once unimaginable. The effectiveness of a telescope is not merely about magnification, but also about resolving power, the ability to distinguish between closely spaced objects. This is largely determined by the diameter of the telescope's mirror or lens. The larger the diameter, the more detail it can resolve. As telescopes grow in size and sophistication, our ability to observe and analyze the universe's most distant and faintest objects continues to expand, revealing an ever deeper understanding of the cosmos. In the grand tapestry of human knowledge, the contributions of the last century to the field of astronomy stand as monumental achievements. Each new discovery peels back another layer of the universe's mysteries, allowing us to glimpse the infinite depths of space and time. As technology continues to evolve and our understanding of the universe expands, the next century promises even greater revelations, promising to rewrite the very story of the cosmos. As we venture deeper into the cosmos, propelled by telescopes and advancing technologies, our understanding of the universe has been irrevocably transformed. These discoveries don't merely redefine what we know, they stretch the very limits of possibility. The journey through space has become a quest not only for knowledge, but for the unraveling of mysteries that challenge our perceptions of time, space, and existence itself. One of the most groundbreaking revelations was the discovery of the expanding universe. This pivotal moment in astronomy began with a simple observation: the redshift in light from distant galaxies. The deeper we peer into the vast expanse, the clearer it becomes that galaxies are moving away from us, receding in every direction. This evidence, first observed in the early 20th century, laid the groundwork for one of the most significant theories in modern science, the Big Bang theory. The idea that the universe originated from a singular, incredibly dense and hot state and has been stretching outward ever since completely reshaped how we view the cosmos. Dating back to the 1920s, this theory has remained a cornerstone in cosmology, influencing everything from the formation of galaxies to the ultimate fate of the universe. The confirmation of the Big Bang theory received a tremendous boost in 1965 with the discovery of the cosmic microwave background radiation, CMB. This faint, almost uniform glow permeates the universe and is considered the afterglow of the Big Bang itself. Imagine witnessing a snapshot of the universe just 380,000 years after its explosive birth, before stars, planets, and galaxies had taken shape. The CMB serves as an imprint of the universe's infancy, providing irrefutable evidence of the universe's hot, dense beginnings and its rapid expansion. This momentous discovery marked a key chapter in our cosmic journey, offering a window into the universe's earliest moments. Then came the enigma of black holes, objects that have long captured the human imagination. The idea of such mysterious, gravitationally intense regions in space, where not even light can escape, was first predicted by Albert Einstein's general theory of relativity in the early 1900s. However, it wasn't until 1971 that the first black hole, Cygnus X1, was confirmed. This discovery was a monumental leap in our understanding of the universe's most mysterious phenomena, opening up an entirely new field of research. Today, black holes continue to captivate scientists and lay people alike, drawing us into their singularities, where the laws of physics as we know them begin to break down. The exploration of exoplanets, the planets orbiting stars beyond our solar system, has been another thrilling chapter in our quest to understand the universe. The discovery of the first exoplanet in 1992, orbiting a pulsar, was a stunning revelation. Yet, it was the 1995 discovery of an exoplanet orbiting a sun-like star that truly ignited interest in this new frontier of astronomy. Since then, thousands of exoplanets have been discovered, with astronomers identifying a dazzling array of worlds. These discoveries have radically altered our understanding of planetary systems, suggesting that planets may be far more common in the universe than previously imagined. The search for habitable exoplanets and the possibility of life beyond Earth continues to drive much of the scientific community's efforts today. Another pivotal moment came with the launch of the Hubble Space Telescope in 1990. This extraordinary instrument has provided some of the most stunning and important images of the universe ever captured. From uncovering the true age of the universe to revealing the existence of dark energy, an enigmatic force accelerating the expansion of the cosmos, the Hubble telescope has been instrumental in pushing the boundaries of human knowledge. Its contributions to our understanding of distant galaxies, stars, and planetary systems have been nothing short of revolutionary. In more recent years, a new breakthrough has emerged: gravitational waves. First detected in 2015, these ripples in the fabric of space-time are caused by some of the most cataclysmic events in the universe, such as the collision of black holes. Their discovery confirmed a major prediction of Einstein's theory of general relativity and opened up an entirely new way of observing the cosmos. Gravitational waves offer a glimpse into phenomena that until now were invisible to traditional telescopic observation. This new method of listening to the universe promises to reveal hidden aspects of cosmic events, allowing us to witness the universe in ways we never thought possible. With each new discovery, we continue to push the boundaries of our knowledge, uncovering the mysteries of the universe that stretch back to its very birth. The journey is far from over, and with each new revelation, we move closer to understanding the vastness of space, the forces that shape it, and our place within it. The universe, with all its complexity and wonder, remains a source of endless fascination, a reminder of just how much is left to discover. Theoretical models are the very framework upon which our understanding of the universe stands, offering profound insights that reach far beyond the limits of our current observational technology. They act as a bridge between what we can observe and the realms of possibility that stretch far beyond our senses, enabling scientists to predict events and phenomena that have yet to be observed while offering explanations for those that have already been detected. These models are the language of the cosmos, grounded in the rigid structures of mathematics and physics. They govern everything from the behavior of the tiniest particles to the formation of the most majestic celestial bodies in existence. One of the cornerstone theoretical models that has shaped our understanding of the universe is the Standard Model of particle physics. This comprehensive framework details the fundamental particles and forces that constitute all matter. Through it, scientists have predicted the existence of particles long before they were ever detected, such as the iconic Higgs boson, which was discovered in 2012. The discovery of this particle was nothing short of a triumph for theoretical physics. It provided the missing link in the mechanism that gives particles mass, an extraordinary confirmation of a prediction made decades earlier. The Higgs boson's discovery highlighted the profound power of theoretical models to guide empirical research and shape our knowledge of the universe's fundamental laws. But the realm of the cosmos is also shaped by monumental models such as Einstein's theory of general relativity. Far more than just a theory about gravity, general relativity offers a groundbreaking vision of the universe. It suggests that gravity isn't merely a force that acts between masses, as Isaac Newton had proposed, but a distortion of space-time itself caused by mass and energy. This revolutionary idea has led to a cascade of predictions, such as the bending of light by gravity, known as gravitational lensing, the strange orbit of Mercury, and the existence of black holes. These phenomena were once thought to be theoretical curiosities, but today they are confirmed tangible aspects of our universe. Furthermore, general relativity was foundational in expanding our understanding of cosmic expansion and predicting the existence of gravitational waves. Einstein's predictions were proven correct nearly a century later, when these waves were detected for the first time in 2015, solidifying the theory as one of the most successful models in the history of science. As we delve deeper into the universe's vastness, theoretical models continue to guide us, especially when we begin to examine large-scale structures and the evolution of the cosmos. The Lambda CDM model, for example, incorporates the presence of dark matter and dark energy, two of the most mysterious and yet influential components of the universe. This model offers an intricate explanation for the distribution and formation of galaxies, the cosmic microwave background radiation, and the accelerating expansion of the universe itself. Through powerful numerical simulations based on this model, astronomers have been able to recreate the universe's evolution, tracing it from the first moments after the Big Bang to the vast structure of galaxies and clusters we see today. These simulations not only provide insight into the formation of these structures, but also allow scientists to investigate how the universe will evolve in the distant future. Theoretical models are also critical in explaining phenomena that are currently beyond our observational reach. For instance, theories of cosmic inflation propose that the universe underwent a period of rapid expansion in the moments following the Big Bang. This theory explains several unresolved cosmological puzzles, including the remarkable uniformity of the cosmic microwave background radiation. While direct evidence of inflation remains elusive, the theoretical framework continues to hold up against existing observational data and remains a guiding force in the search for new empirical evidence. The relationship between theoretical models and observational data is not static. Instead, it is a dynamic, iterative process that pushes the boundaries of human knowledge. Models serve as predictive tools, guiding the design of experiments and shaping the questions we ask about the universe. Yet, it is the unexpected discoveries, those that challenge our existing theories, that push us to refine our models, leading to the development of new, more sophisticated frameworks. This interplay is at the heart of scientific discovery, about driving the forward momentum of cosmology and continually reshaping our understanding of the universe. In astrophysics, simulations play a vital role in helping scientists explore the mysteries of the universe that are beyond direct observation. These digital models, created through advanced computational methods, allow researchers to simulate and study the behaviors of galaxies, stars, planets, and other celestial objects over time. Through these intricate simulations, scientists can test their theories, observe hypothetical scenarios, and gain insight into the processes that govern the universe. These digital cosmoses, though not physical, are vital laboratories for understanding the complex and ever-evolving nature of the universe. Thus, theoretical models are not just abstract constructs, they are the essential tools through which we unlock the universe's secrets. They allow us to peer into realms that no telescope can reach, offering a bridge between the known and the unknown, guiding us toward discoveries that continue to reshape our understanding of the cosmos. Astrophysicists, by inputting the laws of physics and initial conditions into complex simulations, can watch cosmic events unfold within a virtual universe. This allows them to gain insights into the mysteries of the cosmos that would otherwise remain hidden. What makes these simulations so powerful is their ability to manage the immense complexity and the vast scales of space and time, which are intrinsic to astrophysical phenomena. Take the formation of galaxies, for example. This process spans billions of years and is driven by a delicate interplay of gravity, gas dynamics, star formation, and feedback from colossal supernovae and supermassive black holes. Such events can be recreated in simulations, enabling scientists to tweak parameters like the density of dark matter or the rate of star formation, and observe how these changes impact the evolution of galaxies. These digital experiments not only reveal how our galaxy and its neighbors came to be, but also provide clues about how they will evolve in the future. Simulations are also crucial for testing our understanding of the universe's large-scale structure. One of the most significant concepts in this realm is the cosmic web. This vast network of interconnected dark matter filaments forms the backbone of the universe, with galaxies and clusters of galaxies residing at its nodes. Astrophysicists have extensively studied the cosmic web through simulations, refining their models by comparing them to real-world observations from telescopes and surveys. By doing so, they can improve their understanding of dark matter and the forces shaping the cosmos. In the realm of planet formation and the search for extraterrestrial life, simulations offer an invaluable window into the processes that lead to the birth of planets and their atmospheres. These models allow researchers to simulate various scenarios of planetary formation around stars, explore the conditions that could foster habitable environments, and even predict the potential signs of life that future space missions might detect. This theoretical foundation is pivotal in guiding the design of telescopes and missions aimed at finding Earth-like planets and studying their atmospheres. But the power of simulations extends far beyond the birth of planets. They also play a critical role in modeling cosmic cataclysms, events that shake the very fabric of space-time. Supernovae, black hole mergers, and galaxy collisions can be modeled in remarkable detail, enabling researchers to predict the gravitational waves produced by these events, the elements forged in the intense fires of supernovae, and even the mesmerizing dance of galaxies as they merge over billions of years. These predictions are then tested against real observations, giving scientists a powerful tool to validate or refine their theories about the universe's most energetic and enigmatic events. Ultimately, simulations serve as an indispensable bridge between theory and observation. They offer a controlled environment in which the laws of physics can be tested against the infinite complexities of the cosmos. Through these digital universes, astrophysicists are not just exploring the universe's past and present, they are predicting its future. These simulations push the boundaries of human knowledge, bringing us closer to understanding the vast and intricate universe that surrounds us. As we continue to model the birth and evolution of galaxies, we deepen our connection to the cosmos itself. The process of creating these virtual universes is an exciting fusion of art and science, where the laws of physics meet the incredible precision of computational modeling. It is this fascinating endeavor that allows us to glimpse the birth of galaxies, offering a breathtaking window into their monumental formation. Through simulations, we are uncovering the vast mysteries of the cosmos, one digital experiment at a time. In this fascinating field of astrophysics, researchers have developed sophisticated models that begin by simulating the very earliest moments of the universe, right after the Big Bang. These models evolve forward in time, allowing scientists to witness how galaxies may have formed and transformed over billions of years. The complexity of galaxy formation is driven by numerous factors, including the distribution of dark matter, the cooling and condensation of gas into stars, the creation of black holes at the centers of galaxies, and the profound feedback from stars and supernovae. These events can propel gas out of galaxies, thereby influencing the rate of star formation. At the core of these models lies the meticulous work of astrophysicists who employ both theoretical frameworks and cutting-edge numerical simulations. The power of these simulations lies in their ability to create virtual universes within supercomputers. In these digital universes, every particle represents an essential component of the cosmos: dark matter, gas, stars, and beyond. These simulations rely on equations derived from the fundamental laws of gravity, thermodynamics, and hydrodynamics, guiding the way these particles interact over time. By adjusting the initial conditions and physical laws that govern the simulated universe, researchers can simulate a wide range of scenarios. This provides a unique opportunity to explore how various factors shape galaxy formation, comparing the resulting models with real-world observations from telescopes to validate their accuracy. A key player in these simulations is dark matter, a mysterious and invisible substance that doesn't emit, absorb, or reflect light, but still exerts gravitational forces on visible matter. Dark matter is believed to make up about 85% of the total matter in the universe and is essential for the formation of galaxies. It serves as the gravitational scaffold around which galaxies are built. In order to simulate the role of dark matter, astrophysicists often rely on observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe just 380,000 years after its inception, revealing the early distribution of matter. As these simulations progress, dark matter begins to clump together, drawn by gravity, eventually forming dense regions known as dark matter halos. These halos serve as the gravitational wells into which gas falls, cools, and condenses, eventually leading to the birth of stars and galaxies. The process of star formation is far from simple, however, and is heavily influenced by various feedback mechanisms. For example, supernova explosions and winds from massive stars can expel gas from galaxies, thereby curbing further star formation. These complex feedback loops are carefully modeled as they play a pivotal role in the evolution of galaxies. Astrophysicists continuously refine these galaxy formation models as they gather new data from astronomical observations. The ability to study distant galaxies provides scientists with a remarkable glimpse into the past, enabling them to see galaxies as they appeared billions of years ago. This time travel capability is essential for validating and improving existing models, offering critical tests of their predictions. The more detailed our observations become, the more accurate and refined our models of galaxy formation will be, bringing us closer to understanding the complex processes that have shaped our universe. In the end, these simulations represent a powerful tool that allows us to unravel the mysteries of the cosmos. As we continue to collect data from distant galaxies and refine our computational models, we move ever closer to answering one of the most profound questions in science. How did the galaxies, stars, and planets that fill our universe come to be? Despite the tremendous advancements made in our understanding of the cosmos, there are still vast, unsolved mysteries that continue to challenge our understanding of the universe. These questions don't just stretch the limits of our knowledge. They could reshape our fundamental understanding of physics, astronomy, and even the very nature of reality. Among these great unknowns, there are a few that stand out for their profound implications, particularly in relation to the nature of dark matter and dark energy. Firstly, consider the enigmatic nature of dark matter. Despite constituting around 85% of the total matter in the universe, dark matter remains invisible. It neither emits nor absorbs light, making it undetectable by conventional means. The only way scientists can infer its presence is through its gravitational effects on visible matter, primarily through the way it influences the motion of galaxies and galaxy clusters. The fact that it has yet to be directly detected raises one of the most intriguing questions in cosmology. What exactly is dark matter? Various potential candidates have been proposed, such as weakly interacting massive particles, WIMPs, and axions, but despite decades of searching, none have yielded conclusive evidence. The question persists, and the quest to unlock the true nature of dark matter continues to be a fundamental challenge for modern physics. Equally perplexing is the mystery of dark energy, which constitutes approximately 70% of the universe's total energy. Dark energy is believed to be responsible for the accelerated expansion of the universe, a finding that completely upended our previous understanding of cosmic dynamics. For years, scientists believed that gravity would gradually slow the expansion of the universe. But the discovery of dark energy has revealed that something is driving this expansion faster and faster. Despite being a dominant force in the universe, the exact properties of dark energy remain elusive. Understanding what dark energy is and how it behaves could completely transform our view of the universe's future and its ultimate fate. Yet, this mystery persists, making dark energy one of the most profound, unsolved questions in cosmology. Another critical mystery revolves around the universe's rate of expansion, known as the Hubble constant. Recent measurements of the Hubble constant from observations of distant galaxies and the cosmic microwave background radiation have yielded conflicting results, suggesting that our current models of the universe might be incomplete. This discrepancy between different methods of measuring the expansion rate suggests that there could be new physics at play, perhaps related to dark matter, dark energy, or even entirely unknown factors that influence the universe's expansion. Resolving this discrepancy is essential, as it holds the key to understanding the true structure and evolution of the cosmos. The origins of the universe, specifically the conditions that led to the Big Bang, remain one of the most intriguing puzzles in cosmology. According to the theory of cosmic inflation, the universe underwent a period of rapid, exponential expansion in the first fractions of a second after the Big Bang. This inflationary period set the stage for the universe as we know it, shaping the distribution of galaxies and the large-scale structure of the universe. However, the exact mechanism that triggered inflation remains unclear. There are competing models, and while the theory itself is widely accepted, no consensus has emerged on what exactly initiated this rapid expansion or how it unfolded. Perhaps the most fundamental puzzle lies in the asymmetry between matter and antimatter in the universe. According to theoretical models, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated upon contact, leaving only energy behind. However, the universe we observe today is overwhelmingly composed of matter, with very little antimatter to be found. This apparent imbalance points to a mysterious and as yet unexplained asymmetry in the laws of physics. Understanding why this imbalance occurred could reveal profound insights into the fundamental forces that govern the early universe and may provide clues to the deepest questions of particle physics and cosmology. As we venture into these mysterious realms of dark matter and dark energy, we encounter the most intriguing aspects of modern cosmology. These invisible forces of the universe, dark matter and dark energy, challenge the boundaries of our understanding in ways that are both humbling and awe-inspiring. Dark matter, making up around 85% of the universe's total matter, remains an elusive force. It cannot be seen, touched, or even directly detected by light. Yet its presence is felt through its gravitational pull on galaxies and clusters of galaxies, suggesting that this invisible substance plays a critical role in the overall structure of the universe. Similarly, dark energy, despite constituting most of the universe's energy content, remains shrouded in mystery. Its effects are clear, driving the accelerating expansion of the universe, but its true nature remains one of the greatest unsolved puzzles in modern science. Understanding these invisible forces and how they shape the universe could have profound implications, not just for cosmology, but for our very understanding of the laws that govern the universe. The search for dark matter and dark energy continues to drive much of the research in modern physics, and as technology advances, so too will our ability to explore these cosmic mysteries. Until then, the search for answers will continue to challenge our intellect and imagination, pushing the boundaries of what we know about the universe, our place in it, and the very fabric of reality itself. Galaxies spin with an astonishing velocity, far faster than expected, given the amount of visible matter they contain. This suggests the presence of an unseen force, one that binds the cosmos together in ways we cannot yet fully comprehend. This mysterious force is what we call dark matter. Despite its inability to be seen, dark matter is essential to the fabric of the universe. It plays a pivotal role in shaping the structure of galaxies, holding them together and influencing their very formation and movement. The true nature of dark matter remains one of the most perplexing and unresolved questions in modern science. Various candidates for dark matter have been proposed, including weakly interacting massive particles, WIMPs, and axions. These theoretical particles might be the missing link to understanding the cosmos, but so far, no experiment has managed to directly detect them. Scientists around the globe are working tirelessly, from deep underground detectors to high-powered particle accelerators in hopes of finally capturing these elusive particles. Yet the mystery endures, much like the shadowy presence that it is. Dark matter may be invisible, but its effects on the universe are undeniable, from the orbits of galaxies to the very expansion of space. Even more elusive than dark matter is dark energy, a force that accounts for roughly 70% of the universe's energy content. Unlike dark matter, which clumps together and influences galactic structures, dark energy is uniformly distributed across the cosmos. It is responsible for the accelerated expansion of the universe, a discovery that took the scientific world by surprise in the late 1990s. This mysterious force has a repulsive effect, pushing galaxies apart in a way that directly contrasts with the attractive force of gravity. Understanding how dark energy works is crucial to unraveling the ultimate fate of the universe. Whether it will cause the universe to expand forever, eventually slow down, or collapse remains an open question. The nature of dark energy is deeply controversial and under intense investigation. One prominent theory connects dark energy to the cosmological constant, a term first introduced by Albert Einstein in his equations of general relativity. Einstein once referred to this term as his biggest blunder, believing it was unnecessary. However, after the discovery of dark energy, the cosmological constant gained new significance as a potential explanation for the mysterious repulsive force driving the expansion of space. Yet, scientists remain uncertain whether dark energy is truly constant, as originally proposed, or if it fluctuates over time. Some theorists argue that it could be a form of vacuum energy, while others suggest it could be a manifestation of a completely unknown field or force. Together, dark matter and dark energy form the backbone of the cosmic web, shaping the universe's structure and governing its rapid expansion. These unseen forces are the invisible architects of the cosmos, dictating the flow of galaxies and the very nature of space-time itself. But even as we learn more about them, we are left with fundamental questions that remain unresolved. As we peer deeper into the cosmos, the mystery only grows. Could there be other universes beyond our own, each with its own set of physical laws and constants? This captivating possibility, known as the multiverse theory, proposes that our universe is just one of many, each one a separate entity with its own version of reality. The idea of a multiverse is no longer confined to the realm of science fiction, but is now a serious contender in the field of cosmology and theoretical physics. The multiverse theory arises in part from the framework of cosmic inflation. Cosmic inflation suggests that immediately following the Big Bang, the universe underwent an explosive expansion, smoothing out the observable cosmos. Some versions of inflation, however, propose that this process could be eternal, happening in different regions at different times, creating multiple bubble universes. Each of these bubbles would be a separate universe with its own distinct set of physical laws and properties. This mind-bending vision of the multiverse is rooted in the very mathematics of inflation theory, suggesting that the universe we know is but one bubble in an infinite sea of others. Moreover, string theory, which attempts to unify quantum mechanics and general relativity, further supports the multiverse idea. According to string theory, the fundamental building blocks of the universe are not point particles, but tiny, vibrating strings. These strings vibrate in different ways, giving rise to different particles and forces. The landscape of string theory is vast, with many potential solutions, each representing a unique set of physical laws and constants. This implies the existence of a multiverse, where each possible solution corresponds to a different universe. The multiverse theory also offers a potential solution to one of the biggest puzzles in cosmology, the fine-tuning of the physical constants in our universe. The precise values of constants, like the speed of light or the strength of gravity, are perfectly calibrated to allow for the existence of life. In a multiverse, this fine-tuning could be the result of an infinite number of universes, each with its own set of laws and constants. In this vast cosmic landscape, we just happen to live in the universe that supports life as we know it. As scientists continue to explore these profound mysteries, the universe seems more enigmatic than ever before. With every discovery, we are reminded just how much there is yet to understand. Some physical constants, such as the strength of gravitational force and the mass of the electron, appear to be finely tuned in a way that makes life possible. But why are these constants precisely what they are? Could it be mere coincidence, or is there a deeper reason behind it? One of the most intriguing answers comes from the multiverse theory, which posits that our universe is just one of many. In this vast collection of universes, each with its own set of physical laws and constants, it's not surprising that at least one, our own, provides the right conditions for life. According to this theory, there could be an infinite number of universes, each different from the other, making our own seemingly improbable existence not so improbable after all. This notion is closely tied to what's known as the anthropic principle, a statistical argument that suggests the reason we find ourselves in a universe conducive to life is simply because we are here to observe it. In other words, we are able to notice the fine-tuning of the universe's constants because we exist in a universe where those constants allow life. It's a mind-bending idea, yet it offers a framework that explains why the universe appears to be so perfectly suited for life. However, the multiverse theory, despite its compelling logic, remains shrouded in mystery and controversy. It stands on a foundation of speculation, as the nature of these other universes, each one causally disconnected from our own, places them beyond the realm of direct observation or experimentation. This means that testing the theory through traditional scientific methods is not possible. In this sense, the multiverse theory treads the fine line between physics and philosophy, offering tantalizing solutions to some of our most profound questions about existence, while simultaneously challenging our ability to provide empirical evidence. The very structure of the multiverse theory forces us to reconsider the boundaries of science itself. If there are universes that exist beyond our observational reach, can they still be considered part of the scientific discourse? And if we can't observe them, what does it mean for our understanding of reality? These questions reveal the deep philosophical underpinnings of the theory, raising important discussions about the limitations of human knowledge and the role of science in explaining the universe. Thus, while the multiverse theory provides an intriguing possible explanation for the fine-tuning of our universe, it also forces us to confront the limits of empirical science. It may offer profound answers, but only if we are willing to accept that some of the deepest questions about existence may forever remain beyond our grasp. The multiverse, in all its grandeur, may ultimately be a mystery we can never fully solve. Gravity. The weakest yet most pervasive of the fundamental forces, it wields an influence so profound that it shapes the very structure of our universe. This invisible force governs everything, from the tiny particles that make up matter to the majestic dance of galaxies across the cosmos. Described by Einstein's general theory of relativity, gravity is the curvature of space-time caused by mass and energy, a phenomenon that dictates the motions and evolution of celestial bodies. But gravity's reach extends far beyond the mere movements of stars. At the heart of its power lies its role in the formation of the universe itself. After the Big Bang, the cosmos was an almost uniform, hot soup of particles. As the universe expanded and cooled, minute fluctuations in density began to form. These tiny variations, enhanced by gravity's pull, drew in gas and dust, eventually leading to the birth of the first stars and galaxies. These newborn structures acted as gravitational wells, attracting even more material, merging with other clouds of matter and creating the vast cosmic web of galaxies we observe today. However, gravity's influence is far from limited to the birth of galaxies. It continues to shape their behavior and interactions. Galaxies, like distant islands in the ocean of space, are drawn together by their mutual gravitational attraction. These galactic groupings form intricate clusters and are connected by massive filaments of dark matter. Dark matter, which makes up about 85% of the universe's total mass, may not interact with light, but its gravitational pull has a profound effect on the formation of structures on the grandest scale. It remains invisible to our direct observation, yet it guides the vast cosmic architectures that stretch across the universe. Gravitational forces also lead to some of the most awe-inspiring events in the universe. When galaxies collide, it's not a destructive force at play, but a transformative one. The merger of these cosmic giants sparks the birth of new stars. Gas clouds within colliding galaxies compress and ignite, giving rise to brilliant new stellar nurseries. Our own Milky Way galaxy is on a collision course with the Andromeda galaxy, and in about 4 billion years they will merge, forever changing the structure of our home galaxy. This event, like so many others, is a testament to gravity's relentless pull and its role in shaping the destiny of the universe. At an even grander scale, gravity governs the very dynamics of the universe, constantly interacting with dark energy, a mysterious force accelerating the universe's expansion. While gravity pulls structures together, dark energy pushes them apart. The cosmic balance between these two forces determines the future of the universe itself. Will it continue to expand indefinitely, with galaxies drifting further and further apart? Will it slow, eventually halting its expansion and collapsing back on itself in a dramatic big crunch? Or is there yet another fate that awaits the cosmos? Only gravity and its interplay with dark energy will reveal the answer. Gravity's role doesn't end with the cosmic scale. It plays a central part in the life cycles of stars. It's gravity that first compresses gas and dust into dense regions that eventually ignite into stars. Within the cores of stars, gravity creates the immense pressure and heat necessary for nuclear fusion, the process that powers stars and forms the heavier elements that make life possible. But stars are not eternal. When a star runs out of nuclear fuel, gravity will once again take center stage. The star collapses in on itself, leading to a spectacular supernova explosion or the formation of a neutron star or black hole, objects so dense that not even light can escape their powerful gravitational grip. On a more familiar scale, gravity is the force that keeps our planet and all planets orbiting their respective stars. It binds moons to planets, dictates the trajectories of comets and asteroids, and shapes the very tides on Earth. The pull of the moon in particular creates daily rhythms in our oceans, while the sun's gravity ensures our world stays in orbit, providing the conditions for life as we know it. One of the most fascinating effects of gravity is gravitational lensing, a cosmic phenomenon that acts as a natural magnifying glass. When light from distant objects passes near a massive object like a galaxy or cluster of galaxies, its path bends, creating distorted images of the distant source. This effect, predicted by Einstein's theory of general relativity, allows us to peer further into the universe, revealing parts of the cosmos that would otherwise remain hidden, obscured by the vastness of space. Gravity, the unseen force that connects us all, is the ultimate architect of the universe. It shapes galaxies, forms stars, dictates the behavior of celestial bodies, and determines the fate of the cosmos. From the smallest particles to the grandest galaxies, gravity's influence is all-encompassing, and its mysteries continue to reveal the profound interconnectedness of the universe. As we look to the stars, we are reminded of the power of this humble force, which, despite being the weakest of the fundamental forces, is the true master sculptor of everything we know. Gravitational lensing, in many ways, operates like an optical lens, bending and warping light in a manner that magnifies, distorts, and occasionally even multiplies the image of distant objects. This fascinating phenomenon serves as a powerful observational tool for astronomers, offering them the ability to study the universe in ways previously thought impossible. The true beauty of gravitational lensing lies in its potential to unveil the hidden mysteries of the cosmos, especially those that would otherwise remain beyond our reach. By magnifying light from far-off galaxies, those so distant that their light would be too faint to detect with conventional telescopes, gravitational lensing acts as a cosmic amplifier. This ability provides scientists with a unique opportunity to delve into the characteristics of these distant galaxies, including their structure, rate of star formation, and overall composition. By examining these properties, astronomers gain valuable insights into the early universe, helping us understand its origins and evolution on a deeper level. Gravitational lensing, however, does not stop at revealing distant galaxies. It also plays a crucial role in uncovering the enigmatic presence of dark matter. Dark matter, a substance that cannot be seen through direct observation because it does not emit, absorb, or reflect light, remains one of the most significant puzzles in modern astrophysics. Yet its presence is indirectly confirmed by its gravitational influence. The mass of dark matter bends light, leaving an imprint on the lensing effect. Through this phenomenon, astronomers can map out the distribution of dark matter around galaxies and clusters, offering essential clues about its mysterious nature and the role it plays in shaping the universe's structure and evolution. This connection between gravitational lensing and dark matter is one of the most groundbreaking aspects of modern astronomy. Gravitational lensing is typically classified into three main categories: strong lensing, weak lensing, and microlensing. Strong lensing is the most dramatic, producing highly visible distortions such as Einstein rings, arcs, and multiple images of the same galaxy. These striking visual effects are caused by the bending of light from distant objects by massive foreground objects, making them invaluable for studying distant galaxies and galaxy clusters. Weak lensing, on the other hand, subtler, but no less significant. It subtly alters the shape of background galaxies on a larger scale, providing a statistical means of measuring mass distribution in foreground structures. Though these distortions are harder to detect, their cumulative effect reveals important information about the matter between the observer and the distant galaxies. Finally, microlensing occurs when a single star passes in front of another, temporarily increasing the brightness of the background star. This fleeting event can reveal objects that are otherwise too dim to detect, opening new avenues for the study of exoplanets and other faint celestial objects. One of the most exciting and practical applications of gravitational lensing lies in the search for exoplanets and the study of dark energy. As light from distant stars is bent by the gravitational field of intervening objects, astronomers can detect planets orbiting stars in our galaxy. This method, which takes advantage of the lensing effect, provides an alternative way to find planets that might otherwise go unnoticed by conventional means. Similarly, gravitational lensing offers astronomers a way to track the evolution of mass distribution in the universe, a crucial step toward understanding dark energy. Dark energy, a mysterious force believed to be driving the accelerated expansion of the universe, is one of the most perplexing phenomena in modern cosmology. By studying how gravitational lensing reveals mass distribution, scientists can glean vital information about dark energy and its role in shaping the universe's fate. In parallel with the wonders of gravitational lensing, black holes remain among the most captivating and elusive objects in the universe. These regions in space possess gravity so intense that not even light can escape. The formation and evolution of black holes push our understanding of physics to its limits, challenging existing theories and inspiring new ones. Black holes typically form through the collapse of massive stars. When a star several times more massive than our sun runs out of nuclear fuel, it can no longer generate the pressure needed to resist the gravitational forces pulling inward. As a result, the star's core collapses under its own gravity, and if the star is massive enough, the collapse continues until it forms a singularity, an infinitely dense point where the laws of physics, as we understand them, break down. The boundary surrounding this singularity, beyond which nothing can escape, is known as the event horizon. This boundary marks the point of no return for any matter or light that crosses it. The size of a black hole is directly proportional to its mass. More massive black holes possess larger event horizons, and as more mass collapses into the singularity, the black hole grows in size. Stellar black holes, the most common type, form when individual stars collapse under their own weight. However, black holes can also grow in size through a process called accretion, where they pull in material from their surroundings. This process can lead to the formation of supermassive black holes, behemoths that reside at the centers of most galaxies, including our own Milky Way. These supermassive black holes can have masses millions to billions of times greater than that of our sun. The study of black holes continues to captivate scientists as they attempt to unlock the mysteries of these fascinating objects. As black holes grow by accreting matter, they can produce powerful jets of particles and radiation. These emissions, which arise from the interaction between the black hole's magnetic field and the material surrounding it, are still not fully understood. However, it is thought that the spin of the black hole plays a key role in the creation of these jets. These jets can have profound effects on their surroundings, influencing star formation and the evolution of galaxies. By studying the evolution of black holes, astronomers hope to learn more about the universe's deepest secrets, including the complex relationship between black holes, galaxies, and the forces that shape our universe. Black holes, those enigmatic giants of the cosmos, are often seen as the ultimate vacuum cleaners of space, pulling everything into their depths, never to return. However, what if I told you these seemingly all-consuming behemoths can actually shrink and vanish over time? This phenomenon, called Hawking radiation, is named after the brilliant physicist Stephen Hawking, who first proposed it. And here's where it gets mind-bending. According to Hawking's groundbreaking theory, black holes are not completely black. Instead, they emit tiny amounts of thermal radiation, a process that occurs near the event horizon, the boundary from which nothing can escape. This radiation, caused by quantum effects at the microscopic scale, carries away energy, causing the black hole to lose mass. Over unfathomably long periods, this process could lead to a black hole's eventual evaporation. However, before you picture black holes fading away anytime soon, it's important to understand just how slow this process is. For most black holes, particularly the supermassive ones found at the centers of galaxies, this evaporation is an incredibly slow process. The rate at which they lose mass through Hawking radiation is minuscule compared to the vast timescales over which they gather mass from their surroundings. In fact, for most black holes, the effect is almost negligible when compared to their overall lifespan. The cosmos is full of extraordinary phenomena, and while black holes may one day evaporate, the time it would take for them to do so is almost beyond human comprehension. Life, as we understand it, is not a random occurrence, but the result of an intricate interplay of chemical, physical, and environmental conditions. These factors converge in a delicate balance that allows for the emergence and sustenance of biological organisms. Without these conditions, life, as we know it, would not exist. At the core of our exploration into the conditions necessary for life is the concept of the habitable zone, often referred to as the Goldilocks zone. This is the region surrounding a star where the temperature is neither too hot nor too cold, but just right to allow liquid water to exist on a planet's surface. Water, in its liquid form, is essential for life on Earth. It serves as the solvent where the vast majority of biochemical reactions occur. Without liquid water, the complex processes that sustain life simply wouldn't be possible. But it's not just the presence of water that makes a planet habitable. The planet must also have the right atmosphere to support life. An atmosphere does far more than just provide the air we breathe. It shields life on the planet from harmful cosmic radiation and intense solar radiation. It also helps regulate temperature by trapping heat, creating a stable environment that allows for life to flourish. But perhaps most importantly, an atmosphere contains the essential gases required for life processes. On Earth, for example, oxygen is a crucial element for most organisms, while carbon dioxide is indispensable for photosynthesis, the process that powers the Earth's food chain, nourishing plants and indirectly supporting all life on the planet. But the role of atmosphere and water alone is not enough to explain the complexity of life. Chemical elements in their varied forms provide the foundation for life itself. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are the primary building blocks that make up the molecules essential to life: nucleic acids, proteins, carbohydrates, and lipids. These elements combine to form the vast array of molecules needed for the diversity of biological processes. What makes carbon especially important is its ability to form stable, long chains. This unique trait allows carbon to act as the backbone for organic molecules, making it central to the very structure of life. Energy is another critical factor. On Earth, the primary source of energy for life is the sun. Plants capture sunlight through photosynthesis and convert it into usable energy, which forms the foundation of almost every food chain. However, life on Earth has also shown incredible adaptability. In extreme environments, such as near hydrothermal vents deep in the ocean, scientists have discovered organisms that survive by chemosynthesis, using chemical reactions rather than sunlight to generate energy. This discovery has radically expanded our understanding of what constitutes a habitable environment. It suggests that life could, in theory, exist in places devoid of sunlight, provided that there is another suitable energy source. For life to thrive and evolve into more complex forms, stability is key. Abrupt changes in temperature, radiation, or atmospheric composition can disrupt life's delicate balance, making it impossible for organisms to survive or adapt. Therefore, planets with stable orbits, consistent climates, and protective magnetic fields are more likely to provide the long-term conditions needed for life to evolve and endure. In this way, the stability of a planet's environment is just as important as the presence of water and oxygen. As we continue our quest to understand the conditions that support life, our focus has shifted beyond Earth and into the far reaches of the universe, to exoplanets orbiting stars in distant galaxies. The discovery of exoplanets, planets that exist outside our solar system, has revolutionized our search for extraterrestrial life. Scientists now focus on identifying planets within the habitable zones of their stars, where liquid water might exist. These planets are prime candidates for further study, as they could possess the critical conditions required for life to form. The mere possibility of finding another Earth-like planet teeming with life is a concept that fuels our imagination and scientific ambition. The discovery of thousands of exoplanets has opened up new avenues for exploration. Many of these planets orbit stars much like our own sun, and a significant number lie within their star's habitable zone, where liquid water could be present. The potential for life on these distant worlds raises profound questions about our place in the universe. Could life exist elsewhere in the Milky Way? The question remains elusive, and despite years of searching, definitive evidence of extraterrestrial life has yet to be found. But the mere prospect has inspired incredible advances in technology and a renewed sense of wonder. Our galaxy, the Milky Way, is home to hundreds of billions of stars, many of which likely have planets in orbit around them. Some of these planets may possess the right conditions for life, and with every new discovery, we edge closer to answering one of humanity's most enduring questions. In the years to come, we will continue to push the boundaries of what is possible, exploring new planets and environments, searching for the elusive signs of life beyond Earth. This journey, fueled by curiosity and determination, may one day answer the question that has captivated humanity for centuries. Are we truly alone in the universe? And yet, the quest for habitable worlds is far more complex than merely identifying a habitable zone. It involves the intricate dance of multiple factors, each one playing a pivotal role in determining whether a planet can support life. Yes, the location of a planet relative to its star is crucial, but the story doesn't end there. The planet's atmosphere, magnetic field, and geological activity also factor heavily into its potential to foster life. For instance, the atmosphere is more than just a blanket of gases. It serves as a life-saving shield, protecting potential organisms from the harmful effects of cosmic rays. It also provides the essential gases like oxygen and carbon dioxide that are vital for biological processes. Then there's the magnetic field, which acts as the planet's defense system against solar winds, preventing the loss of its atmosphere. Beyond these protective measures, the geological activity of a planet ensures that life has the ingredients it needs to survive. It recycles vital elements, providing a stable climate and promoting the necessary chemical processes for life's survival. Astrobiology, the fascinating field dedicated to understanding the origin, evolution, distribution, and future of life, takes a multidisciplinary approach to unravel these mysteries. By combining knowledge from astronomy, biology, geology, and chemistry, scientists work to uncover the conditions under which life can arise and persist. As part of their research, they study some of the most extreme environments on Earth, such as deep-sea hydrothermal vents and barren deserts, which host life forms in conditions once thought to be inhospitable. These earthbound analogs provide invaluable insights into how life could endure in similarly extreme environments elsewhere in the cosmos. Indeed, one of the most groundbreaking avenues in the search for extraterrestrial life lies in the analysis of exoplanetary atmospheres. By studying the light that filters through a planet's atmosphere as it passes in front of its parent star, astronomers can detect the signature of key gases, oxygen, methane, and carbon dioxide, that, on Earth, are strongly associated with biological processes. This method, known as spectroscopy, opens the door to a deeper understanding of distant worlds, potentially identifying planets where life might thrive. In the coming decades, new telescopes and space missions will refine this technology, enabling even more precise measurements and bringing us closer to identifying signs of life light years away. While the search for life beyond our solar system is an exhilarating pursuit, the exploration of our own cosmic backyard remains just as thrilling. Robotic missions to Mars, Europa, and Enceladus, the icy moons of Jupiter and Saturn, are taking us closer to understanding whether microbial life could exist or may have once existed in these distant environments. Beneath the frozen crusts of Europa and Enceladus, subsurface oceans lie hidden, ancient, possibly habitable environments that could harbor life, either in the present or past. The river valleys and lake beds of Mars further intrigue scientists as they point to a time when the red planet may have once had liquid water on its surface, offering a potentially life-sustaining environment. As we venture further into the stars, it's becoming increasingly clear that the universe is teeming with possibilities. The Milky Way alone contains billions of planets, many of which reside in their star's habitable zone. The absence of direct evidence for life elsewhere doesn't negate its possibility. Rather, it fuels the sense of excitement and wonder. Each discovery brings us a step closer to answering the most profound question humanity has ever asked. Are we truly alone in the universe? The search for extraterrestrial life, as ambitious as it is, involves a multi-pronged approach. One key method revolves around the discovery of exoplanets, worlds orbiting stars beyond our sun. Scientists have developed sophisticated techniques to detect these distant planets, such as the transit method, which measures the dimming of a star's light as a planet crosses in front of it. Another method, radial velocity, detects the subtle gravitational tug a planet exerts on its star, revealing the planet's mass and orbit. These methods provide crucial insights into the characteristics of these exoplanets, factors such as their size, orbital distance, and most importantly, their location within their star's habitable zone. However, we aren't stopping there. Advancements in technology are allowing us to study the very atmospheres of these distant worlds. By analyzing the light passing through an exoplanet's atmosphere, scientists can detect molecules that could indicate the presence of life. Oxygen, methane, and water vapor, key ingredients for life on Earth, are now being searched for in the atmospheres of distant exoplanets, signaling potential habitats for life. And then there's the direct exploration of planets and moons within our solar system. Robotic missions have ventured to Mars seeking signs of past or present microbial life, and more are planned. These explorations aim to uncover the secrets of the Martian soil and atmosphere, potentially unlocking the mystery of whether life ever took root on our neighboring world. The search extends to the outer solar system, to the icy moons of Jupiter and Saturn, moons like Europa and Enceladus, which harbor subsurface oceans beneath their icy surfaces. Could these oceans, cut off from the harsh conditions above, provide the necessary environment for life to thrive? In the grand scheme of things, the search for life beyond Earth is only beginning. Every new mission, every new piece of technology, brings us closer to the day when we might look to the stars and answer humanity's oldest question. As our exploration continues, one thing is certain: the universe, vast and full of mysteries, may hold the key to understanding the very nature of life itself. And so we embark on missions that venture into the unknown, collecting invaluable data about the moons of our solar system. These expeditions are driven by a relentless quest to understand the composition, geology, and potential hydrothermal activity of these distant worlds. In doing so, they explore environments where life might just be waiting to reveal itself. As we peer deeper into these frozen moons, scientists are uncovering evidence of subsurface oceans and geothermal processes that may harbor life hidden beneath layers of ice. These fascinating discoveries fuel our curiosity about the possibility of life elsewhere in the cosmos. But while these missions focus on finding life in our own solar system, another pursuit is underway, reaching farther into the vast expanse of space. This is the search for extraterrestrial intelligence, or SETI. Rather than focusing on physical exploration, SETI listens. Using sophisticated radio and optical telescopes, it scans the heavens for signals that might be the unmistakable signs of advanced civilizations. These signals are thought to be intentionally crafted, sent from faraway stars by technologies far beyond our own. SETI researchers search for these deliberate messages, or they examine the stars for unusual phenomena, such as the presence of megastructures, enormous artificial structures that could warp the light from their host stars, signaling the presence of an intelligent civilization. Yet, despite decades of searching, no definitive proof of intelligent extraterrestrial life has surfaced. Still, the search is far from over. With each passing year, the methods grow more refined as researchers expand their searches into new wavelengths and utilize more sensitive instruments. As technology advances, the hope of finally hearing that long-awaited signal from another world grows ever stronger. Beyond these targeted efforts, scientists are also casting a wider net, exploring unconventional avenues for discovering life in the universe. Among the most promising of these are meteorites. Some of these ancient space rocks, found right here on Earth, are believed to have originated on Mars. When examined, they reveal traces of complex organic molecules, building blocks of life that could hint at past biological activity on the red planet. Could life once have thrived there? Or could these molecules have journeyed from other worlds, carried across the vastness of space to seed new possibilities? Even the vast clouds of gas and dust that float between the stars are not beyond the reach of our curiosity. In these interstellar clouds, scientists have discovered complex organic molecules as well. These molecules, fundamental to life as we know it, are scattered throughout the universe, suggesting that the raw materials for life might be more widespread than previously imagined. If these complex compounds can form in the cold depths of space, it's not such a stretch to imagine that life might emerge in similar conditions, given the right set of circumstances. As we push the boundaries of exploration, the question remains, are we alone? The search continues, guided by the hope that one day we will find the answer to one of humanity's most profound mysteries. The cosmic web is an awe-inspiring, vast tapestry that stretches across the universe, serving as its skeletal structure. This sprawling, intricate network is composed of galaxies, galaxy clusters, and vast clouds of intergalactic gas, all bound together by unseen filaments of dark matter. Spanning billions of light years, it resembles a delicate web of interconnected cosmic threads, with dense nodes of galaxies linked by long, dark strands of matter surrounding vast, empty voids. This immense architecture of the universe is more than just a physical structure. It is the framework through which the cosmos itself evolves. But what is dark matter? Dark matter is an elusive and invisible substance, making up about 85% of the universe's total mass. It does not emit, absorb, or reflect light, rendering it invisible to conventional telescopes. Yet its presence is unmistakably felt through its gravitational influence on visible matter, such as galaxies and galaxy clusters. Moreover, dark matter reveals itself through a fascinating phenomenon called gravitational lensing, where the immense gravitational pull of dark matter distorts the path of light from distant galaxies, bending it around the invisible structure of the cosmic web. The genesis of this cosmic web traces back to the earliest moments of the universe, shortly after the Big Bang. In the epoch of cosmic inflation, the universe expanded at an astonishing rate, stretching the tiny quantum fluctuations of matter into vast macroscopic scales. These minute irregularities in the fabric of the universe were the seeds of the cosmic web, laying the foundation for the network we observe today. As the universe continued to expand and cool, gravity began to magnify these initial density fluctuations, pulling matter together into denser regions and leaving behind vast empty voids. Over billions of years, this process, driven by the invisible hand of dark matter, sculpted the filamentary structure of the cosmic web. The dark matter acted as a scaffolding, attracting visible matter, stars, galaxies, and galaxy clusters, onto its framework. Observations of the cosmic microwave background, CMB, the faint afterglow of the Big Bang, offer a glimpse into the early stages of the universe, providing a snapshot of the cosmos about 380,000 years after its birth. These minute fluctuations in temperature, revealed by the CMB, represent the first traces of structure, marking the regions of higher and lower density that would eventually evolve into the filaments and voids of the cosmic web. These early imprints of the universe's structure provide vital clues about the forces that shaped it. pointing to the fundamental role dark matter played in organizing the matter of the universe. The filaments that make up the cosmic web are not mere wisps of dark matter. They also contain intergalactic gas, dust, and the very building blocks of stars and galaxies. These massive filaments, often spanning hundreds of millions of light years, serve as the sites where galaxies are born and evolve. Gravity pulls matter together in these cosmic highways, guiding the birth and growth of galaxies. Where these filaments intersect, the density of matter becomes especially high, creating the perfect environment for the formation of galaxy clusters and superclusters, the largest and most massive structures in the universe. Studying the cosmic web is not merely an academic exercise. It is essential for understanding the universe's past, present, and future. By mapping this vast network of filaments, astronomers gain invaluable insights into the distribution of dark matter, dark energy, and the forces that govern galaxy formation and evolution. Using advanced techniques such as large-scale galaxy surveys and sophisticated simulations, scientists are unraveling the mysteries of the cosmic web, shedding light on the nature of these invisible forces and helping to refine our cosmological models. These studies not only deepen our understanding of the universe's structure, but also offer profound insights into the nature of reality itself. At the heart of the cosmic web's formation lies dark matter, an invisible yet incredibly powerful force. While dark matter cannot be directly observed, its gravitational effects on galaxies and clusters are undeniable. This unseen substance provides the framework upon which the visible universe is built. As dark matter gathers into dense regions, it exerts its gravitational pull, drawing in baryonic matter, the ordinary matter that makes up stars, planets, and even life itself. This process not only determines the location of galaxies, but also influences their properties, growth, and evolution over time. As we continue to study the cosmic web, it becomes increasingly clear that dark matter's role in shaping the universe is profound and irreplaceable. It is the invisible architect of the cosmos, guiding the formation of galaxies and clusters, shaping their interactions, and influencing their future. The cosmic web, in all its vastness and complexity, is a testament to the unseen forces that govern the universe, and through its study, we inch ever closer to understanding the true nature of the cosmos itself. In the early universe, moments after the Big Bang, matter existed in a nearly uniform distribution. However, this early uniformity was not absolute. Tiny overdensities in the fabric of space began to form, and as time passed, they were amplified by the invisible yet powerful force of dark matter. These overdensities acted as the primordial seeds from which the magnificent cosmic web, our universe's vast interconnected structure, would grow. It was within these dense regions where dark matter's gravitational pull was the strongest that gas and dust began to coalesce. These dense pockets formed the first galaxies, clusters, and superclusters where dark matter filaments intersected, creating deep gravitational wells. These cosmic filaments, like celestial highways, channeled gas and dust through the vast expanse of space toward the intersections or nodes where galaxies would eventually form. As the universe continued to expand and evolve, this process remained dynamic. Galaxies didn't simply form and stop, they continued to attract matter from the surrounding cosmos. This ongoing accumulation of matter triggered new star formations and led to the growth of galaxies over billions of years, shaping the cosmos as we observe it today. The cosmic web's structure had a profound impact on how galaxies interacted with one another. Galaxies embedded in the same filament of dark matter were not isolated. They were drawn toward common gravitational centers, which led to regular interactions and mergers. These mergers, often chaotic and dramatic, were not just random events. They were fundamental processes in the evolutionary history of galaxies. In these collisions, bursts of star formation could occur, rapidly growing galaxies and altering their shape. For instance, the merging of spiral galaxies could result in the formation of elliptical galaxies. The cosmic web was not simply a passive structure. It was an active stage where galaxies were in constant motion, evolving in response to the cosmic forces at play. The distribution of galaxies within the cosmic web also plays a key role in determining their properties. Galaxies in dense regions of the web, such as massive galaxy clusters, tend to be older, redder, and more elliptical. These galaxies have typically exhausted their gas reserves and ceased the process of star formation. On the other hand, galaxies found in the less dense regions or along the filaments themselves are often younger, bluer, and continue to form new stars. This stark contrast highlights the diverse evolutionary paths that galaxies take depending on their environment within the cosmic web. Moreover, the cosmic web's evolution is not solely driven by gravitational forces. It is also shaped by powerful feedback mechanisms. Supernova explosions, for instance, release immense amounts of energy, while active galactic nuclei, AGN, inject heat into their surroundings. These processes can disrupt the collapse of gas into new stars, regulating star formation within galaxies, and even altering the structure of the web itself. Over cosmic time, these feedback processes play a crucial role in maintaining the balance of star formation and the overall evolution of the universe's structure. The evidence for the cosmic web is overwhelming and comes from a range of both observational data and theoretical predictions. One of the most compelling pieces of evidence comes from large-scale galaxy surveys, such as the Sloan Digital Sky Survey, SDSS, which have mapped millions of galaxies. These surveys have uncovered an intricate pattern in the universe's structure. Galaxies are not scattered randomly across the universe. Instead, they are clustered along vast filaments of dark matter, creating a cosmic lattice of interconnected structures. Between these filaments lie vast voids, regions with few galaxies, emphasizing the contrast between the dense structures and the empty spaces between them. Additionally, the invisible presence of dark matter has been detected through gravitational lensing, another significant piece of evidence for the cosmic web. When light from distant galaxies passes near a massive object, like a galaxy cluster, the gravitational pull of that cluster bends the light, magnifying and distorting the image. This phenomenon not only highlights the presence of massive structures along our line of sight, but also maps the distribution of dark matter within these structures. The lensing patterns observed by astronomers align perfectly with the predictions of the cosmic web model, offering a powerful confirmation of the universe's large-scale structure. Thus, the cosmic web is more than just a collection of galaxies and dark matter. It is a vast, dynamic structure that has been shaped by the interplay of gravity, dark matter, star formation, and cosmic feedback mechanisms. Through the merging of galaxies, the continuous flow of matter, and the influence of dark matter, the cosmic web is the very framework that supports the universe's evolution. The evidence for this intricate, interconnected structure is clear, and it offers a window into the deeper workings of the universe on its grandest scales. Cosmological simulations serve as a powerful testament to the existence of the cosmic web, offering a virtual glimpse into the grand architecture of the universe. By harnessing the immense computational power of supercomputers, these simulations recreate the universe's evolution, stretching back from the instant following the Big Bang to the present moment. They are grounded in the fundamental laws of physics and initial conditions drawn from the cosmic microwave background (CMB) observations, allowing scientists to trace the unfolding of cosmic structures with remarkable accuracy. These simulations unveil a striking, web-like network of dark matter filaments interspersed with vast voids. The resulting structures, though initially theoretical, align closely with the observed distribution of galaxies and dark matter. In fact, the patterns emerging from these simulations resonate strongly with the real-world cosmic map derived from extensive astronomical surveys. This alignment provides compelling evidence that the cosmic web is not a mere abstract theory, but a tangible feature woven into the very fabric of the universe. Furthermore, the study of the intergalactic medium, IgM, the faint gas that permeates the space between galaxies, offers further confirmation. Observations of distant quasars, whose light travels across vast stretches of space, have revealed distinct absorption lines in their spectra. These lines, formed when hydrogen gas in the IgM absorbs light at specific wavelengths, correspond precisely to the predicted locations of cosmic filaments. As the light from these quasars passes through the IgM, the absorption features map the presence of hydrogen gas in regions that align with the theoretical filaments of the cosmic web, offering yet another piece of the puzzle to the structure of the universe. Through both simulation and observation, the cosmic web's existence is increasingly undeniable. What was once a speculative model has now become a confirmed aspect of the universe's design, intricately connecting galaxies across unimaginable distances. The expansion of the universe is not a simple matter of galaxies racing away from a central point, as many might imagine. Instead, space itself is expanding, carrying galaxies along with it. This concept can be difficult to grasp, but one useful analogy is that of a balloon with dots drawn on its surface. As the balloon inflates, the dots move away from each other, not because they are physically moving through space, but because the space between them is stretching. This analogy illustrates how galaxies can appear to move apart without implying any central point of origin from which everything is retreating. The key takeaway is that it is the fabric of space itself that is expanding, not the galaxies flying outward in all directions. One of the most compelling pieces of evidence for this expansion comes from the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. The CMB provides a snapshot of the universe when it was just 380,000 years old, offering a glimpse into the early, hot, and dense state of the cosmos. The uniformity and even distribution of the CMB across the sky support the theory that the universe has been expanding ever since the Big Bang, cooling and spreading out over billions of years. This observation aligns with the idea that the universe started from a single, hot, dense point and has been gradually expanding into the cooler, more diffuse space we see today. At the heart of this cosmic expansion is the Hubble constant, a number that quantifies the rate at which galaxies are moving away from us per unit of distance. For decades, this constant has been a key parameter in cosmology. However, precise measurements have shown a fascinating discrepancy. The value derived from observations of the early universe, such as those of the CMB, does not exactly match the value determined from measurements of the local universe, such as those of supernovae in nearby galaxies. This tension hints at something deeper about the nature of the universe, possibly suggesting the need for new physics or a refinement of current models to reconcile these differences. Moreover, the expansion of the universe is not merely continuing, it is actually accelerating. This startling discovery, made in the late 1990s through observations of distant supernovae, has revolutionized our understanding of the cosmos. Scientists have since come to attribute this acceleration to a mysterious force called dark energy, a repulsive force that permeates all of space and counteracts the force of gravity. While the exact nature of dark energy remains one of the biggest unsolved mysteries in cosmology, it is believed to make up about 70% of the universe's total energy content. Dark energy is driving the universe to expand at an ever-increasing rate, and this phenomenon challenges our fundamental understanding of the laws of physics. The continuing expansion and acceleration of the universe have profound implications for its ultimate fate. If dark energy continues to dominate, the universe could expand forever, slowly becoming colder and emptier in a scenario known as the Big Freeze. In this future, galaxies, stars, and even planets would be so far apart that new star formation would cease, and the universe would gradually fade into darkness. Alternatively, if the properties of dark energy were to change, other possibilities could arise, such as the Big Crunch, where the universe collapses back in on itself, or the Big Rip, a catastrophic scenario in which galaxies, stars, and even atoms are torn apart by the accelerating expansion. As the universe expands, it also shapes the evolution of galaxies, determining how they form, interact, and ultimately meet their end. The expansion itself has far-reaching effects on these cosmic structures. On the largest scales, the expansion ensures that galaxies are moving away from each other. This was first observed by Edwin Hubble in the 1920s, and it became known as Hubble's law. The relationship is simple. More distant galaxies are receding faster than those closer to us. A popular analogy compares the expanding universe to a loaf of bread rising in the oven. As the dough expands, raisins, representing galaxies, move further apart. This phenomenon is uniform. Every galaxy observes other galaxies moving away from it, with the speed at which they move correlating with their distance. However, this grand expansion does not mean that galaxies are always getting farther apart everywhere. In fact, within local groups or clusters of galaxies, gravitational attraction is strong enough to overcome the effects of cosmic expansion. Our own Milky Way, for example, is gravitationally bound to the Andromeda Galaxy and other members of the local group. Despite the overall expansion of the universe, these galaxies are not drifting away from one another. Instead, they are on a collision course, bound together by their mutual gravitational pull. In the distant future, the Milky Way and Andromeda will collide, merging into a single, larger galaxy, proving that gravity can still hold sway over the vast distances of space. In summary, the expansion of the universe is one of the most significant and awe-inspiring discoveries of modern cosmology. From the cosmic microwave background to the accelerating expansion driven by dark energy, the universe is revealing its secrets at an astonishing pace. And as we continue to observe and measure its growth, it becomes clear that the universe's fate is deeply tied to the properties of dark energy and the dynamics of space itself. Whether we are headed toward an ever-expanding, cold, and desolate cosmos, or a dramatic collapse or tear, the journey of the universe remains one of the greatest mysteries of all. Our Milky Way, for instance, is on a captivating trajectory, one that will see it collide with the Andromeda Galaxy in approximately 4 billion years. This is not a mere possibility. It is an inevitable event driven by the forces of gravity, pulling the two galaxies toward one another in an intricate cosmic dance. While the universe at large expands, galaxies within local clusters, such as the Milky Way and Andromeda, are not immune to gravitational forces. They continue to interact, merge, and ultimately form even larger structures, a dynamic that occurs despite the universe's seemingly endless stretch. This expanding universe, however, is far from a one-dimensional phenomenon. It plays a crucial role in shaping the very formation of galaxies. As the fabric of space itself stretches, the distribution of both dark matter and baryonic matter, everything from stars and planets to the very matter that forms life, undergoes profound changes. Dark matter, which remains invisible to our eyes because it does not interact with light, exerts its gravitational influence across vast cosmic distances. This hidden force is the unseen architect of the cosmic web, a network of interconnected filaments and halos that sculpt the galaxies we observe today. The gravitational pull of dark matter is instrumental in guiding the movement of baryonic matter, directing the creation of galaxies along the denser, gravitationally bound regions. As space stretches and galaxies form, the ever-expanding universe also leaves a telltale mark on the light traveling through it, a phenomenon known as redshift. This is where the story of light becomes even more fascinating. As light from distant galaxies journeys toward Earth, the expansion of space stretches the very wavelengths of this light, shifting them toward the red end of the spectrum. This shift isn't just a scientific curiosity, it's a critical tool for astronomers. By studying the redshift of light from far-off galaxies, scientists are able to measure the rate of the universe's expansion and peer into the distant past. This redshift phenomenon provides a unique window into the infancy of galaxies, thus offering us a glimpse into the universe shortly after the Big Bang, when stars and galaxies were just beginning to form. The future of our universe, as it continues to expand, depends on the mysterious and powerful force known as dark energy. If the current acceleration of expansion continues, as our observations suggest, the distant galaxies will slowly fade from view. Their light will be stretched to wavelengths so long that they will become undetectable. In this future scenario, the universe will transform into a much lonelier place. Galaxies, isolated in their respective clusters, will drift further apart as the cosmos continues to expand, leaving vast voids between them. In this lonely expanse, only the closest galaxies will remain visible, and the universe as we know it will be forever changed. Magnetic fields, though invisible to the naked eye, are the silent architects of the cosmos, intricately woven into the very fabric of the universe. These fields, once considered secondary players in the vast theater of space, are now recognized as essential forces that drive a multitude of astrophysical processes, shaping stars, planets, galaxies, and even the very structure of intergalactic space. Though they remain hidden from our eyes, their influence extends across all scales, from the smallest particles to the largest cosmic structures. In the hearts of stars, including our very own sun, magnetic fields are born from the celestial dance of dynamo action. Within these stellar furnaces, electrically charged fluids, plasma in particular, move in a tumultuous, convective manner, generating magnetic fields that reach out into space. These powerful fields give rise to some of the most dramatic phenomena in the solar system. Sunspots, those dark blemishes on the sun's surface, are manifestations of intense magnetic activity, as are the awe-inspiring solar flares and coronal mass ejections. These eruptions of magnetic energy can have tangible effects on Earth, from disrupting satellite communications to inducing geomagnetic storms that can damage power grids. Yet they also paint the skies with the stunning beauty of auroras, a natural light show caused by the interaction of charged particles with Earth's magnetic field. On a larger scale, magnetic fields are not merely bystanders in the formation of stars, but rather key players in shaping their birth and evolution. The cold, dense molecular clouds of gas and dust, the stellar nurseries where stars are born, are influenced by magnetic fields from the moment they begin to collapse under gravity. These fields can regulate the rate at which new stars are formed, influence their initial mass distribution, and even direct the flow of gas and dust in the surrounding protostellar disks that ultimately give birth to planets. As stars evolve, magnetic fields continue to play a critical role, guiding the dynamics of the interstellar medium, the diffused gas and dust that fills the space between stars. These fields help stabilize the medium, preventing its collapse under gravity, and they channel the flow of charged particles across the galaxy, influencing everything from star formation to the distribution of matter. Magnetic fields extend their reach beyond individual stars to the very structure of galaxies. In the vast reaches of intergalactic space, where galaxies drift apart and interact, magnetic fields play an equally important role. Within galaxy clusters, the largest gravitationally bound structures in the universe, magnetic fields are amplified by the chaotic motion of the intracluster medium. These fields stretch across millions of light years, impacting the behavior of cosmic rays, charged particles that zip through space at nearly the speed of light. They influence the propagation of these rays, which travel from one end of the universe to the other, and in doing so, help shape the cosmic landscape. The origin of these cosmic magnetic fields, particularly those that permeate the voids between galaxies, remains one of the great unsolved mysteries of astrophysics. It is believed that these fields may have been seeded during the early stages of the universe, arising from processes that unfolded in the wake of the Big Bang. Over eons, they have been amplified by dynamical processes, but their precise origins are still the subject of intense research. Understanding the nature of these primordial fields could unlock valuable insights into the early universe's conditions and the mechanisms that have driven the evolution of cosmic structures over time. However, despite their profound impact, magnetic fields are notoriously difficult to study. They cannot be observed directly as we observe light or other electromagnetic radiation. Instead, astronomers must rely on indirect methods, such as the polarization of light or the behavior of charged particles, to trace the presence and strength of these invisible forces. Advancements in observational technology and theoretical models are slowly unraveling the secrets of cosmic magnetic fields, allowing us to glimpse the hidden forces that shape our universe. These fields, though unseen, are proving to be as dynamic and influential as any of the stars and galaxies they help form. In the intricate process of star formation, magnetic fields are not passive observers. They are active forces, guiding the collapse of molecular clouds and influencing the formation of protostellar disks. As these clouds of gas and dust contract under gravity, magnetic fields interact with the charged particles, subtly influencing the collapse's speed and direction. In some cases, magnetic fields act as a support against gravity, preventing certain regions from collapsing and elongating the cloud in others. This not only affects how quickly stars are born, but also the size and mass distribution of those stars. As the collapse progresses, the magnetic field lines become more concentrated, guiding the flow of material onto the emerging star. This magnetic regulation helps control the star's growth, ensuring that it forms in a way that is consistent with the surrounding conditions. Furthermore, these fields play a key role in shaping the protostellar disk, the rotating disk of gas and dust that surrounds a young star. This disk, which will eventually give rise to planets, is influenced by the magnetic field, which can direct the flow of material, shaping the dynamics of planet formation. Thus, magnetic fields are not merely passive elements in the cosmos. They are active, invisible forces that shape the universe at all scales, from the birth of stars to the evolution of galaxies and the behavior of cosmic particles. Understanding their role in these processes is crucial for a deeper comprehension of the universe's structure and evolution. Magnetic fields, though hidden from view, are truly the unsung forces that shape the cosmos. And these disks, silent, swirling formations of gas and dust, are more than cosmic leftovers. They are the birthing grounds of planets, the fertile cradles where new worlds are forged from chaos. Within these protoplanetary disks, invisible architects are at work. Magnetic fields, threading through the material like unseen fingers, transport angular momentum outward, allowing matter to spiral inward toward the embryonic star at the center. This delicate dance not only feeds the growing star, but also sets the stage for the assembly of planetary systems. As magnetic fields shape the evolution of these disks, they may govern everything from the formation of gas giants to the subtle sculpting of orbital paths. But the influence of magnetic fields does not end at the scale of solar systems. On the grand canvas of the cosmos, where galaxies ignite and evolve, they remain an omnipresent force. Though their precise role in the initial birth of galaxies is still debated, their influence on galactic evolution is undeniable. Magnetic fields weave through the interstellar medium, orchestrating the movement of charged particles, shaping clouds of gas, and influencing where and how stars are born. They guide the flow of matter into and out of galaxies, subtly regulating the engines of stellar creation and galactic growth. Beyond the boundaries of individual galaxies lies a more enigmatic arena: galaxy clusters. Here, magnetic fields span vast intergalactic distances, forming intricate webs through the searing plasma of the intracluster medium. In these environments, they affect the trajectories of cosmic rays and shape the dynamics of billion-degree gas that drifts between galaxies. These fields, though invisible, leave fingerprints in shock waves and turbulent eddies, influencing not only the thermal history of the cluster, but also the fate of galaxies orbiting within it. Over time, they contribute to the vast and slow evolution of cosmic structure on the largest scales known. Yet, studying these magnetic fields remains one of the great observational challenges in astrophysics. Because we cannot see them directly, scientists rely on their influence on light and matter. The polarization of light, subtly altered as it passes through magnetized space, offers clues. So does synchrotron radiation, the telltale signature of electrons spiraling along magnetic field lines at near-light speeds. With the help of these techniques and ever more sophisticated computer simulations, astronomers are now able to model the cosmos with increasing fidelity, capturing the elusive influence of magnetic fields across space and time. In this unfolding story of cosmic evolution, magnetic fields emerge not as passive threads, but as active, dynamic agents, quiet forces that shape stars, mold galaxies, and trace the hidden order behind the visible universe. The interstellar medium, ISM, is not merely a quiet expanse between stars, but a dynamic and fascinating environment that connects the stars and drives the processes that shape galaxies. It is an intricate mix of gas, dust, and cosmic rays, filling the vast, seemingly empty spaces between stars. This medium, far from being a mere void, is instead a vibrant participant in the cosmic cycle, playing an essential role in star formation, stellar evolutions, and the very fabric of the universe. Comprising roughly 99% gas and 1% dust by mass, the ISM is composed of a variety of elements. The bulk of the gas is hydrogen, present in both atomic and molecular forms, with helium and trace amounts of heavier elements such as carbon, nitrogen, and oxygen. The dust, made up of microscopic solid particles, contains compounds like silicates, carbon-based molecules, and even more complex organic molecules, substances that could one day lead to the emergence of life itself. It is in this complex and varied medium that stars are born, evolve, and ultimately die, enriching the galaxy with the elements necessary for future generations of stars, planets, and possibly life. The ISM is a constantly changing environment, its physical conditions varying wildly from one region to another. Temperatures in the ISM can range from less than 100 Kelvin in the cold, dense molecular clouds, where star formation occurs, to well over 1,000,000 Kelvin in the hot, ionized regions that surround massive stars and supernova remnants. These wide-ranging conditions create a rich and varied landscape of environments within the ISM. For instance, molecular clouds are the coldest and densest parts of the ISM. These regions, often referred to as stellar nurseries, are where new stars are born. The Orion Nebula, one of the most famous molecular clouds, is visible to the naked eye and is a hub of new star formation. H2 regions are areas of ionized hydrogen gas surrounding young, hot stars. The ultraviolet light from these stars strips electrons from hydrogen atoms, resulting in vast, glowing clouds of gas that shine brightly across the universe. Warm neutral and warm ionized mediums are areas of moderate temperature where the gas can be either neutral or ionized. These regions make up a substantial portion of the ISM's volume and are crucial for the transition of gas between different phases. Hot ionized medium refers to the extremely hot ionized regions produced by supernova explosions. These vast regions, which can extend for hundreds of light years, are key to understanding the energy balance of the ISM and the recycling of materials throughout the galaxy. The ISM is not just a collection of gas and dust, it is also threaded with magnetic fields and permeated by cosmic rays, high-energy particles that travel through space at nearly the speed of light. These cosmic elements interact with the gas and dust in fascinating ways, shaping the ISM's structure and behavior. For example, magnetic fields can guide the flow of gas, influencing how clouds collapse and form new stars. Cosmic rays, on the other hand, contribute to the ionization of the ISM and drive chemical reactions within molecular clouds, altering the composition of the material within them. The cycle of matter within the ISM is one of the most fundamental processes in the universe. Stars are born from the dense gas in the ISM, and as they age and die, they return materials to the medium. Stellar winds, planetary nebulae, and supernova explosions all eject matter back into the ISM, enriching it with heavier elements. These elements are then incorporated into future generations of stars, planets, and potentially life. It is through this process that the ISM is slowly but steadily transformed, as each generation of stars adds new layers of complexity to the interstellar mix. Ultimately, the ISM is not just the backdrop against which stars are born. It is a vital participant in the creation of the cosmos itself. Without the materials and conditions provided by the ISM, star formation would not be possible. The medium plays a crucial role in facilitating the delicate dance between gravity, gas, and dust, setting the stage for one of the universe's most essential processes, the birth of stars. Star formation begins in the densest regions of the ISM within molecular clouds. These cold, dark clouds contain a mix of molecular hydrogen, helium, and dust, along with heavier elements and organic molecules. The frigid temperatures and the shielding effect of dust grains allow these clouds to maintain the low energies necessary for molecules to form and persist. The process of star formation begins when certain regions of a molecular cloud begin to collapse under their own gravity, pulling in gas and dust to form dense cores. These cores, as they condense, will eventually ignite to form new stars, continuing the cycle of matter in the ISM. This interaction between gas, dust, and gravity forms the bedrock of the ISM's role in the universe, where the birth, death, and rebirth of stars occur continuously. Every star, from the smallest red dwarf to the largest supergiant, is formed from this very medium, an ongoing process that shapes the galaxy, drives cosmic evolution, and lays the foundation for life as we know it. In this cosmic dance, the ISM is both a cradle and a recycler, ensuring that the universe remains in a constant state of renewal. Without it, the stars and all that they create would not exist. This fundamental cycle is what makes the ISM just an interesting feature of the galaxy, but a driving force behind the very structure and future of the cosmos. The universe is full of dynamic processes, each contributing to the intricate web of creation and destruction that shapes galaxies. Among these processes, the formation of stars is one of the most fascinating and mysterious. The birth of a new star begins in the cold depths of molecular clouds, vast and dense regions of gas and dust scattered throughout the interstellar medium, ISM. These clouds are the lifeblood of galaxies, where new stars and planetary systems are conceived. But what sets this incredible process into motion? External pressures can trigger the collapse of these clouds in remarkable ways. Supernova shockwaves from massive stars exploding nearby send ripples through space, disturbing the gas and dust. The gravitational pull from passing stars or the pressure exerted by ionization, fronts created by massive stars, can also provoke the collapse. Once this process begins, the cloud begins to fragment into smaller clumps, each with the potential to form one or more stars. As these fragments contract, the conservation of angular momentum causes them to spin faster, flattening into rotating disks around nascent stars, protostellar disks. These protostellar disks are vital not only for the formation of stars, but also for the creation of planets. As gas and dust accumulate within the disk, the material begins to clump together, eventually leading to the formation of planets, moons, and other celestial bodies. In essence, these disks are the birthplaces of solar systems, where the raw materials for planetary systems are crafted. Yet, the birth of stars is not a straightforward process. Throughout the collapse of the cloud, the ISM's magnetic fields and cosmic rays play critical roles in shaping the outcome. Magnetic fields can slow down or even channel the collapse of gas, altering the rate at which stars form and influencing the initial mass distribution of stars. On the other hand, cosmic rays penetrate the densest parts of molecular clouds, ionizing gas and facilitating complex chemical reactions. These reactions contribute to the intricate chemistry found within star-forming regions, where new molecules are created, some of which may even form the building blocks for life. Despite these conditions, the efficiency of star formation is surprisingly low. Only a small fraction of the gas within a molecular cloud ends up being converted into stars. The majority of the material is dispersed back into the ISM through processes like stellar winds, radiation pressure, and supernova explosions, particularly from the most massive stars. These stars, after their death, enrich the ISM with heavier elements that were forged in their cores, providing the necessary building blocks for future generations of stars. In turn, this feedback mechanism can trigger further rounds of star formation, perpetuating the cycle of stellar birth, life, and death within galaxies. Nebulae, the vast and luminous clouds of dust, hydrogen, helium, and other ionized gases, stand at the forefront of this incredible cycle. Known as the nurseries of the universe, these nebulae are where new stars are born. Their glowing beauty, visible to the naked eye under the right conditions, offers a breathtaking glimpse into the cosmic forces at work. These awe-inspiring clouds are not merely beautiful to look at, they are also key players in the evolution of galaxies. The word nebula itself comes from the Latin word for cloud, perfectly capturing the ethereal, diffuse nature of these celestial formations. Nebulae vary greatly in size and shape, each playing a distinct role in the grand life cycle of stars. Emission and reflection nebulae, often the sites of star formation, are where the raw materials of the galaxy, gas, dust, and energy, coalesce under gravity, giving birth to new stars. As stars form, they begin to ionize the surrounding gas, emitting radiation that further influences the nebula and its development. In contrast, dark nebulae, dense clouds of dust and gas, serve as the birthplaces for future stars and planetary systems. These dense clouds are not as luminous as their glowing counterparts, but they are just as vital. When the material within a dark nebula collapses under its own gravity, it can form protostars, which over time will ignite and become new stars. This process continues the cycle of stellar evolution, where each new generation of stars forms, burns brightly, and eventually dies, scattering its enriched material back into the ISM to fuel the creation of new stars. Thus, the contribution of the ISM to the ongoing process of star formation is far more than just a backdrop. It is an active, dynamic participant in the birth of stars, planets, and the very structure of galaxies. The ISM, with its complex interplay of gas dynamics, magnetic fields, cosmic rays, and stellar feedback, shapes the future of the universe. It is here, in these vast, ever-evolving nebulae, where the seeds of stars and solar systems are sown, and where the grand story of the cosmos unfolds. As we draw the curtains on our journey through the unfathomable depths of our galaxy and the vast, mysterious universe beyond, we are left standing at the crossroads of discovery and wonder. With each step forward, countless questions arise, questions that stretch the limits of our understanding and imagination. Can it really be that everything we see, feel, and experience, from the stars above to the very atoms in our bodies, was born from nothing? Or is there something fundamental, an unseen force or hidden dimension that we have yet to uncover. The universe seems to hold its secrets tightly, teasing us with glimpses of its true nature, leaving us to ponder. Are we ready to face the answers, or will we, as a species, ever be capable of truly comprehending the mysteries we might one day uncover? And so, the greatest question of all lingers in the air. What does the future hold for humanity in this grand cosmic journey? Will we rise to the challenge, or will we remain on the edge of the unknown, searching for meaning in the infinite expanse? What do you think? Let us know your thoughts in the comments below, and be sure to subscribe to Starflux for more thought-provoking explorations into the mysteries of the universe. Thank you for watching, and stay curious.